Hello and welcome to Science for Sleep. I'm really glad you're here. Maybe you're listening in the dark, tucked into bed, or resting somewhere quiet, letting the weight of the day fall away. Maybe you've been thinking too much, or maybe not thinking at all, just hoping for a little peace. Wherever you are, this space is for you. A place where science moves gently, and questions don't need quick answers. You can breathe here, you can pause. This isn't a lesson. It's not a lecture. It's something slower, softer, like sitting beside someone and wondering aloud, not to solve, just to notice. The world moves fast enough already. You don't need to, not here. Tonight's story begins with something simple. So simple, in fact, that most of the time we barely notice it. Time. Not what time it is, but what time is. Not the numbers on a screen. Not the voice from your phone saying it's 9:42 p.m. But the thing underneath, the thing those numbers are trying to describe, what even is time. We use it constantly. We chase it. We measure it. We say we have too little or too much of it. But we almost never stop to ask what it really is, or where it comes from, or whether it's the same for everyone, everywhere. That's the question we'll follow tonight. Quietly, patiently, without rushing to find an answer. Does the universe know what time it is? It sounds like the kind of question you might ask half asleep, like something a child might whisper when the room is dark and everything feels a little bigger. But the more you think about it, the more serious it becomes, the more puzzling. Because we live in time. Every breath happens inside it. Every memory sits behind us in it. Every plan leans forward into it. But does the universe keep track of any of that? Does it know when now is? Or is time something we've invented? A way to keep ourselves from getting lost? What time is it where you are? Not on the clock, in your mind. Does it feel late? Does it feel early? Are you in the middle of something or slowly winding down? Sometimes time stretches. Sometimes it disappears. A single minute can feel like an hour, or an entire afternoon can vanish before you know it. We think of time as constant, but our experience tells us otherwise. And it turns out physics agrees. Time isn't fixed. It isn't steady. It bends. It slows. It behaves differently depending on where you are, how fast you're moving, and what's around you. That means your time, right now, might not be the same as someone else's, even if you're side by side. So what does that say about the universe? About how it holds everything together? About whether it even needs time to do what it does? That's where we're going. Gently, carefully. We'll talk about relativity and clocks and why time might not be what we think it is. We'll explore what happens near black holes, what time looked like in the early universe, why your future and your past might be more connected than they seem. But we'll do it slowly, one idea at a time, one quiet question after another. And if this kind of slow science is something you enjoy, if it helps you think more calmly, or even fall asleep, feel free to subscribe or leave a like. It helps this space grow, and it helps others find their way to it too. Now, get comfortable. Let your eyes go soft. Let the day fade back a little. There's nothing to keep up with here. Just listen. Just breathe. You don't have to look far to notice that time doesn't always behave the way we expect. Sometimes it feels like it moves quickly, sometimes slowly. You've had days that vanished before you could catch up with them, and nights that stretched endlessly even though the clock barely moved. That difference between the time we measure and the time we feel is easy to ignore, but it's there, quietly shaping everything. And once you start noticing it, it becomes hard not to ask, is time as steady as we believe? Or are we just used to pretending that it is? This is where the question starts to grow. Not just what is time, but is time the same for everyone? And deeper still, does it exist in the same way for the entire universe? That's where we are now. Not trying to answer that all at once, just sitting with the question, letting it get a little heavier, noticing the strange way it pushes back when you think about it for too long. Start with something familiar, a clock, any clock, the kind on your phone, the one built into your microwave, a wristwatch, a digital timer counting down in a lab somewhere. They all tell time the same way, by breaking it into equal pieces. Seconds, minutes, hours. But what are they actually measuring? Mechanical clocks measure movement, gears turning, pendulums swinging, hands sweeping. Digital clocks rely on electrical pulses or vibrations in crystals. Atomic clocks, the most precise we have, use the vibrations of atoms, incredibly fast and incredibly consistent. But even those aren't measuring time itself. They're measuring change, regular, repeatable change. In physics, that's what time really comes down to, the progression of change, one state becoming another, a system evolving, a signal shifting. It's not a thing you can point to, it's not a substance, it's a relationship between now and later, between before and after. That's where it starts to feel a little unstable. Because once you define time by change, then in places where nothing is changing, what does time mean? If you were floating alone in space, far from stars, far from any motion or sound or light, completely still, how would you know whether a second had passed, a minute, an hour? Without movement or memory, what's left of time? That's not a trick question. It's an actual problem in physics. The answer isn't obvious. Some would say time is still passing. Others would argue time doesn't really apply without events to mark it. It becomes something theoretical, present in the equations, but absent in experience. And that's where we begin to see how different our intuitive sense of time is from the way the universe might actually treat it. Because when you dig into the physics of time, the ground doesn't hold as firmly as you'd expect. Take two clocks, they're identical. One stays with you on Earth, the other you send into orbit, or put on a fast-moving spaceship. When they come back together, they won't agree. The one that moved faster or spent time farther from Earth's gravity will have ticked at a slightly different rate. Not because it was broken, not because it malfunctioned, but because time itself flowed differently for it. This isn't science fiction. This is measured, proven. It's one of the core predictions of Einstein's theory of relativity, and it has been confirmed again and again. According to relativity, time is not absolute. It's not a background constant like a ruler laid out across the cosmos. It's flexible. It depends on speed and gravity. It's affected by motion and mass. And this flexibility isn't a minor detail. It's fundamental. It's the reason GPS systems have to adjust their internal clocks constantly. Satellites in orbit experience time at a slightly different rate than devices on the surface of the Earth. If we didn't account for that, your navigation would drift by kilometers each day. Even small differences in elevation can cause small differences in time. The top of a skyscraper ages slightly faster than the bottom. Your head is, by the tiniest margin, older than your feet. It's strange, but it's real, and it's measurable. So when we ask whether the universe knows what time it is, we have to be careful, because even here on Earth there's no single answer. Time is not the same everywhere. It doesn't tick at the same rate in all locations. It doesn't even tick the same way for all people, not in a physical sense, and certainly not in an emotional one. This brings us to a deeper idea. If time behaves differently depending on where you are and how you move, then maybe it's not time itself that matters, but space-time, the combined structure that links space and time together into one fabric. Einstein's insight was that space and time aren't separate. They are part of the same thing, and that thing bends, it stretches, it curves around massive objects like planets and stars. Those curves don't just affect space, they affect how time flows too. In a way, mass tells space-time how to bend, and that bending tells everything how to move, including clocks, including you, including light. When you stand on the surface of the Earth, you're not just feeling gravity as a pull, you're feeling the shape of space-time. You're resting in a curve, and in that curve, time moves at a slightly different pace than it would in deep space. That's not poetry, that's the geometry of the universe. But the geometry isn't fixed. It depends on what's nearby, on mass, on motion, on energy. So now we're starting to see how difficult the question really is. Does the universe know what time it is? Which time? Whose time? Where? And what would it even mean for the universe to know something? It helps to pull back for a moment and consider how we experience time in the first place. We don't feel the bending of space-time directly. We don't sense relativity. We live in what feels like a steady forward flow. One second after another, one event following the next. That's time as it appears to us, a straight line, a constant rhythm. But relativity tells us that line is only one possible path through a much more complicated landscape. A landscape where different observers can disagree on the order of events, where what's simultaneous for you might not be simultaneous for someone else, where there is no universal now. That might be the hardest part to accept. We like to believe in a shared present, one common timeline unfolding across all of space. But physics doesn't give us that. The laws of the universe allow different regions, different observers, to have their own slices of time, their own clocks, their own sequences. And in that kind of universe, the idea of a single time, a single answer to what time is it, starts to fade. It's not that time disappears, it's just that it becomes local, personal, a property of your motion, your place in the fabric, your journey through space-time. That raises another question. If time is so deeply tied to movement and gravity and location, then what happens in the parts of the universe that are empty? Far from stars, far from motion? Is time still there, ticking quietly in the background? The answer depends on how you define there. One approach is to say yes. Time exists wherever space-time exists. The geometry is still present, even if there's nothing in it. But if there's no change, no observer, no clock, no process to mark it, then time becomes invisible, not absent, but unreachable. There are theories that suggest time might not even be fundamental at all, that it might emerge from deeper processes, quantum events, entanglement, entropy, that it might not be something the universe has, but something that arises when certain conditions are met. It's an idea still being debated, still in development, but it suggests something profound, that time might not be part of the foundation of reality, that it might be a feature of the way we interpret patterns, a shadow cast by change. And if that's true, then the universe wouldn't know what time it is, because time wouldn't be something that exists for it in the first place. It's a hard thought to sit with. We're so used to time being constant, unavoidable, simple. But the more you look at it, the less simple it becomes. Even the idea that time flows forward, that the past becomes the present, and the present becomes the future, isn't guaranteed by the laws of physics. Many equations work the same in both directions. The universe doesn't seem to care whether something happens forward or backward in time, and yet we experience a clear direction, a one-way street. That's something we'll explore more soon. But for now, we're just letting the quiet question settle. What is time, really? And if we can't define it completely or measure it universally or agree on when now is, then what kind of thing is it? That doesn't mean time isn't real. It just means it might not be what we assumed. And maybe that's the point. You're lying still now, in your own moment, your own place in the fabric, your own speed, your own gravity, your own thoughts shifting slowly forward. Someone else, somewhere else might be doing the same, but their clock is ticking just a little differently, not broken, just shaped by where they are. And that difference isn't a flaw. It's part of how time works, part of how the universe is built. So if we ask again, does the universe know what time it is? Maybe the answer is this. It doesn't need to, because there isn't one answer to give, but that's just the beginning. You've probably worn a watch, or glanced at your phone to check the time, or seen the blinking digits of a microwave clock flashing 12 hours after a power outage. It seems obvious that all clocks, if they're working properly, should agree with one another. If they don't, something must be wrong. One of them must be slow, or fast, or broken. But that idea only holds in everyday life, where speeds are low and gravity is steady. In reality, clocks don't always agree, even if they're perfect. And it's not because they're malfunctioning. It's because the universe doesn't treat time as uniform. Start small. Imagine you and someone else each have an atomic clock, the most precise type of clock we've built. You synchronize them. They tick in perfect rhythm, Then you give one clock to a passenger boarding an airplane, and you keep the other one with you on the ground. The plane takes off, flies a few hours, then lands. You meet back up and compare the clocks. They're not the same anymore. The one that flew on the plane has ticked slightly less time than the one that stayed on Earth. It's a small difference, a fraction of a second, but it's real, and it's been measured. Not just once, but over and over. You can even measure it with highly sensitive clocks on mountaintops versus those at sea level. The elevation alone, the change in gravity, is enough to create a measurable time difference. The principle is simple, even if the outcome is strange. Time moves differently depending on how fast you're going and how strong gravity is around you. This is Einstein's theory of relativity at work. Special relativity tells us that when an object moves quickly, especially close to the speed of light, time slows down for it relative to someone who's standing still. General relativity adds something else. Time also moves more slowly in stronger gravitational fields. Gravity curves space, and it bends time with it. On the surface of Earth, we're in a gravitational field. If you were farther away from the planet, say on the International Space Station, you'd experience time just a little faster than someone down below. Again, the difference is tiny. But it's not theoretical, it's real. We build our satellite systems around it. Your GPS would be completely wrong without those corrections. Without accounting for both motion and gravity, your phone could put you miles from where you actually are. So time, as we live it, is not a single stream. It's many streams, each one shaped by the local conditions, each one slightly different. And the more extreme those conditions become, the more obvious the differences are. Let's move farther out, away from the Earth, into deeper space. Imagine an astronaut orbiting near a black hole. They stay just outside the event horizon, the point beyond which nothing escapes. From their perspective, time seems to pass normally. Their heart beats. Their thoughts move. Their clock ticks like it always has. But to someone watching from far away, that astronaut's time slows dramatically. From the outside, it's as if they're moving through molasses. You could watch their clock from afar and see it tick once while yours ticks hundreds of times. Their time is stretched, slowed, dilated, and if they fell inward, crossed the event horizon, the difference would become complete. To them, they'd continue falling, but to you, they'd appear frozen in place. Their last visible moment would hang at the edge of the black hole forever. They'd never quite vanish. From your perspective, time for them would have stopped. This isn't just a curiosity, it changes how we think about reality. Because it means there is no universal time. There's no master clock ticking across the cosmos. There is no shared now that covers every galaxy, every star, every planet. Your now and someone else's now are not guaranteed to line up. Even light, which we often use as a constant reference, doesn't give us a clear global time. It travels at the same speed in a vacuum, always. But it still takes time to move from place to place. When you look at the stars, you're not seeing them as they are. You're seeing them as they were because of how long their light took to reach you. The farther away something is, the older the image. You could be looking at a star that died 1 million years ago. Its light is just arriving now. And while that light was traveling, your clock kept ticking. Your life kept moving. But somewhere else, a different clock ticked at a different rate. The further apart things are, the harder it becomes to say what's happening at the same time. Because simultaneity, the idea that two things happen at once, breaks down when you're moving through different paths in space-time. This is why physics talks about proper time, the time measured along a specific path by a specific observer. It's not universal, it's personal, defined by where you are, how you move, and what gravity is doing around you. In that view, your wristwatch isn't wrong if it doesn't match mine. It's just telling the truth about your experience of time. And mine is telling the truth about mine. It's like being in a vast city where every neighborhood has its own time zone. You might walk across a street and suddenly be 2 seconds ahead of someone next to you. Not because you skipped anything, but because the street itself changed how time flows. In normal life, those differences are too small to notice, but they're always there. And in extreme environments, near neutron stars, in particle accelerators, at the edge of black holes, they become dramatic, obvious, unavoidable. This forces us to rethink the idea of a single timeline, a single history, a shared clock. Because the universe doesn't run on a centralized schedule, it runs on countless intersecting ones. And when we say what time is it, we really mean what time is it here for me right now? You can even see this in the structure of the universe itself. Some regions are older than others, not by birth date, but by experience. They've lived through more or less, depending on how space-time has behaved around them. It's as if parts of the cosmos have aged at different speeds. And this isn't just theory, we can measure it. We've seen time dilation in the decay rates of fast-moving particles. We've observed it in the bending of a light around massive objects. We've watched it unfold in the shifting frequencies of distant signals. Every one of these confirms the same thing. Time is not the same everywhere. So then we're left with a question. Not just what time is it, but whose time are we talking about? And if every clock tells a slightly different story, then the universe itself doesn't have one story. It has many, layered, parallel, woven together by relationships, cause and effect, light signals, gravity wells, but not pinned to a single clock. That might sound unsettling, but it's also freeing. It means time is flexible, adaptable, local. It moves with you. It's part of your path. And it also means there's no cosmic authority watching the clocks, making sure everything stays on schedule. The universe doesn't care about schedules. It cares about relationships, about how things influence each other, how mass affects motion, how events connect. That's the real structure. Not a single ticking clock, but a web of interactions, each with its own pace. You live inside that web, your heartbeat, your thoughts, your memories, all shaped by the local flow of time, and that flow is yours. No one else's is exactly the same. It's strange to think about, but also strangely comforting. Because it means your experience isn't wrong. Even if it doesn't match someone else's, your time is your own, carved by your position, your motion, your place in gravity. And that also means your future isn't fixed. Your timeline isn't locked to a single direction. It can curve, it can stretch, it can slow down. There's a moment that happens when you're standing at the edge of something unfamiliar, something you don't quite understand. You pause. Your body stays still, but your thoughts stretch out ahead of you, trying to make sense of what you're seeing. The moment feels longer than it is. That's where we're going now, into the places where time does something similar. It stretches, not metaphorically, not emotionally, literally. Imagine standing beside something heavy, not just heavy like a building or a mountain, heavy in the sense of mass packed so tightly that its presence bends the very space around it. You don't need to see anything unusual to know it's there. The math tells you. The measurements confirm it. Clocks run differently near it. And this difference isn't a glitch. It's built into the structure of space itself. Take a clock, any kind, even a perfect atomic clock. Place it on the surface of Earth, then take an identical one and move it into orbit just a few hundred kilometers above. The two clocks are exposed to slightly different amounts of gravity. One is closer to the planet's center, where the gravitational pull is stronger. The other is farther away. After some time passes, you compare them. The one farther from Earth will have ticked slightly faster, not because it ran fast, but because time itself flowed faster for it. This phenomenon is called gravitational time dilation, and we see it not only in theory, but in actual systems we use every day. GPS satellites operate in a weaker gravitational field than we do on the ground. Their onboard clocks tick a little more quickly than Earthbound clocks. Engineers have to adjust for that. Without those adjustments, the system would fall out of sync within hours. Your phone wouldn't be able to find your location. Planes would veer off course. The world we've built assumes time is consistent, but the systems keeping it running all account for the fact that it's not. Now, take that same idea and apply it to something far more massive than Earth, a black hole. Black holes don't pull you in like vacuums. They don't suck things toward them like people sometimes imagine. They're just regions where mass has collapsed into such a small volume that the curvature of space-time becomes extreme. You could orbit one safely if you stayed far enough away. But as you get closer, time starts to behave differently. Let's say you could hover just above the event horizon, the boundary beyond which nothing returns. You're not falling in. You're holding position with powerful engines staying at a safe distance. From your perspective, everything seems fine. Your heart beats normally. Your thoughts flow. Your clock ticks forward like it always does. But if someone were watching you from a great distance, they'd see something very different. They'd see your movements slow down, your signals stretch, your clock tick more and more slowly. To them, it would look like you were frozen in time, hovering at the edge of the black hole forever. You wouldn't feel this change. That's important. From the inside, everything would feel the same. But from the outside, time would be stretching. Not just the perception of it, but the structure itself. This isn't speculation. It's predicted by Einstein's equations and supported by everything we know about general relativity. The closer you are to a massive object, the slower time passes for you compared to someone farther away. This leads to some strange possibilities. You could spend an hour near a black hole and come back to find that years had passed for someone who stayed farther out. The difference could be dramatic. Centuries, millennia. It depends on how close you get and how long you stay. That's what time dilation really means. Not just a shift in experience, but a physical change in the passage of time. Your clock and someone else's don't just disagree. They represent different timelines. Both are valid, both are real. But they unfold at different rates because the environment around them bends space-time in different ways. And if time can stretch this way, it raises deeper questions. What exactly is time stretching into? What allows that stretching to happen? And how far can it go? In the framework of relativity, time is one axis of space-time. Just like up, down, left, and right are in space, massive objects don't just bend the space around them, they also bend the direction of time. When you approach a black hole, it's not just that you feel pulled inward, it's that time itself is curving toward the center. Staying still requires enormous energy. Falling inward is the natural path, and as you fall, your time slows relative to the outside world. It's not something you could override. It's not a feature of your perception. It's built into the fabric of reality. The first time this became a topic of public imagination was probably through science fiction. Stories about astronauts returning home to find centuries passed. Ships orbiting massive stars to stretch out time. But the idea comes from real physics. From the fact that gravity, not force in the classic sense but curvature, controls how time flows. In 1976, the Gravity Probe A experiment launched a hydrogen maser clock aboard a suborbital rocket. It flew 10,000 kilometers into space and then fell back. During the flight, scientists compared its timekeeping to a reference clock on Earth. The spaceborne clock ticked slightly faster, exactly as general relativity predicted. The difference was tiny, about 1 part in 10 million, but it was there. Confirmed. Repeated. Built into our models of reality. Now, take that idea to a larger scale. Near the center of our galaxy is a black hole millions of times more massive than our sun. It bends time around it in ways we can't directly experience, but we can observe the effects. We've watched stars orbiting close to that black hole. We've measured how their light shifts, how their paths curve. We've seen that the time those stars live through is not quite the same as the time we experience here. From that, we learn something important. That time is not a universal stage. It's a set of local conditions. It depends on the shape of space-time in each region of the universe. And that shape is not fixed. It changes with motion. It changes with gravity. It changes when mass moves, when energy shifts, when systems evolve. That means time is not just something we travel through. It's something that reacts, something that bends, something that changes shape. We see this in gravitational lensing, when light from distant galaxies is bent around massive objects on its way to us. That bending isn't just a curve in space, it's a shift in time. The light takes longer to reach us. It follows a stretched path. The time it carries is not the time it left with. It's shaped by what it passed through. And now we're starting to build a clearer picture. time is not an absolute measurement, it's a local one. It depends on your path, your environment, your proximity to mass and energy. And because of that, a moment is not a fixed thing either. When you sit in a chair and breathe slowly, your moment is not the same as someone else's. If they're moving quickly, or resting on a mountain, or traveling through space, their moment is slightly different. Their second is not your second. And when you both look back, your timelines won't match up perfectly. That difference won't matter much for most of your life, but it matters for understanding how the universe works, because it means that the idea of a single, global now doesn't hold. The universe doesn't have one clock, it has billions, and they all tell time a little differently. So when time stretches, it's not breaking, it's behaving exactly as the structure of reality tells it to. That idea becomes even more important when we think about the early universe. Right after the Big Bang, when space was hotter, denser, and expanding quickly, the curvature of space-time was extreme. That means time flowed very differently then than it does now. The rate of time was tied to the expansion. The timeline of the cosmos isn't just long, it's uneven. The universe has lived through moments that pass more quickly, or more slowly than ours. And there may be regions now, far from us, cut off by the speed of light, where time flows at a different pace because of different structures, different densities, different gravitational conditions. In that context, the question, what time is it now, becomes impossible to answer for the universe as a whole. There is no now that covers everything. There are only local nows, nearby timelines, threads that move parallel but not in perfect step. And once we accept that, we begin to understand why time seems to stretch. It stretches because the universe is not flat, because gravity is not uniform, because motion is relative, because space-time curves. And that curvature is not just a shape, it's a tempo, it's a rhythm. It's the way each place measures its own passage. You're living in one of those places, your timeline is yours, your seconds are shaped by the planet beneath you. The speed you're moving, the energy around you, you don't feel it changing. But it's changing all the same. And out there, somewhere else, another clock is ticking a little differently. Not faster or slower in a broken way, just different. Because that's what time does. It stretches. Most of the universe is empty. Not in the way a room feels empty, but in the literal physical sense. Between stars, between planets, between galaxies, there are vast stretches of space where almost nothing exists. No air, no light, no sound. Just distance, just vacuum. You might imagine that nothing happens in these places, that they're quiet, still, timeless. But even in the emptiest parts of the universe, time continues to pass. Or at least that's what we assume. Out there, far beyond the edge of our solar system where the sun's gravity begins to loosen its grip, there's no clock ticking in the dark. There's no signal marking the hours. And yet, things still change. Particles drift. Radiation spreads. Gravity pulls faintly on dust that hasn't yet found a home. It's hard to imagine time moving through that kind of silence. There's no rhythm to hold on to, no heartbeat, no light dimming or brightening. But the structure of space-time doesn't disappear just because things get quiet. The geometry remains, and according to everything we know, time continues, slowly, steadily, invisibly. If you sent a spacecraft into that darkness, its onboard clock would keep ticking, its systems would log every second. But those seconds would be different than the ones you experience here. The spacecraft, far from strong gravity, would feel time slightly faster. Just like we discussed before, the deeper into gravity you go, the slower time moves. And out in the interstellar void, gravity is weaker than almost anywhere else. That means the breath between stars, those long cold gaps in the sky, aren't timeless. They're just slow. Slow in a way that's hard to notice, hard to measure, slow in a way that feels like stillness. But even in that stillness, time is still there, and that's important, because it reminds us that time doesn't need activity to exist. It doesn't require a clock or a movement or a sequence of actions. It's part of the framework, it's in the geometry. If space exists, time does too, even when there's no one watching it. That idea becomes clearer when you consider what light does in those spaces. When a star sends out light, that light travels outward in all directions. It doesn't stop when it leaves the star's atmosphere. It doesn't need a medium to move through. It keeps going, through gas clouds, past solar systems, across empty stretches of space that haven't seen matter in billions of years. That light takes time to travel, and we know that because we can measure how long it takes to get from one point to another. From the sun to Earth, about 8 minutes. From the nearest star, over 4 years. From the edge of the observable universe, more than 13 billion years. None of those places are moving with us, but the light still takes time. That suggests time is embedded in the space itself. It's part of the distance, part of the structure, part of the path, which means even if you were floating alone in the middle of that void, far from any source of light, time would still be moving for you. Not because anything is happening, but because your position in space-time still exists. And that position has its own relationship to time. But this also brings up a deeper question. What exactly does it mean for time to move? We often speak about time like it's a flow, like it travels. But in physics, time doesn't move. We move through time. Events unfold. Systems evolve. But time itself isn't a thing that flows across us. It's not a wind. It's not a force. It's a dimension, like height or width or depth. And like those, it has direction, but not motion. So in the space between stars where no events are happening, at least none that we can detect, it might feel like nothing is happening at all. But from the perspective of relativity, time is still unfolding, still mapping out possible futures, still holding a structure that allows motion to resume if something stirs. And sometimes something does stir. Particles drift through interstellar space. Hydrogen atoms, sparse but still present, float through the void. Occasionally a high-energy particle from a distant supernova zips through at nearly the speed of light. Those particles obey time, they decay, they scatter, they interact when they meet resistance. They don't stop moving just because the space is empty. Their paths take time to complete. Even the background radiation of the universe, the faint afterglow of the Big Bang, carries a timestamp. It's stretched and cooled and thinned by billions of years of cosmic expansion. And we can measure how long ago that energy was released. We can track how far it's traveled. The information it carries only makes sense because time passed between its origin and its detection. So even though it feels like the space between stars is a kind of nowhere, it's actually rich with time. It just doesn't look the way we expect. Think about sleep for a moment. When you lie down and close your eyes, you're not doing anything. Not visibly, not physically. But time still passes. You still age. Your body continues to process. Your cells repair. And even when your mind drifts into dreams or deeper, still into dreamless rest, time doesn't stop. It just becomes harder to notice. That's what interstellar space is like. A kind of dream state for matter. Still, slow, but never motionless in the strictest sense. And even in places where no matter exists at all, space-time still holds form. Its curvature is dictated by the energy and mass around it, but even in the absence of mass, the equations still apply. Space without objects still has shape, and shape still means direction, and direction includes time. You can think of it this way. Imagine the universe as a vast stage. Most of the action happens under the lights, where stars burn, where planets orbit, where people think and build and talk. But even in the wings, where no spotlight shines, the floor is still there. The walls still hold their position. The structure is intact. It's not empty in the sense of being nothing. It's empty in the sense of waiting. But space doesn't wait with intention. It doesn't anticipate. It doesn't observe. It simply continues. Its time moves forward not because something tells it to, but because that's how the structure is built. And that time has consequences. If you send a spacecraft into deep space and leave it untouched for 1,000 years, it won't stay frozen. Its components will degrade. Its fuel will break down. Radiation will leak. Its systems will age. Not quickly, but steadily. And when you come back, if you could, it will be older. not just in metaphor, but in measurable time. So now, when we ask whether time exists in the breath between stars, the answer becomes clearer. Yes, it exists, it moves, it matters, but only when something interacts with it. Time is always there, in the same way space is always there. But unless something changes, unless something moves, decays, radiates, or vibrates, it's hard to see that time passing. That doesn't mean it's gone. It just means there's no local witness. We are witnesses. We're built to mark time. Not perfectly, but persistently. We feel hunger, fatigue, memory. We experience cause and effect. And so to us, time is constant. We can't stop feeling it. Even in stillness, we know it's there. That's why the empty spaces of the universe feel so strange. They're missing the markers we're used to. They don't offer the same feedback. There's no rhythm, no reference. But time still works there, quietly, unseen. And eventually, things pass through. A comet on a long arc might spend thousands of years in deep space before being pulled toward a star. Its path obeys gravity. But gravity obeys space-time, and space-time includes time. That's the link. Even when it's hard to feel, time is part of the structure. The breath between stars isn't a pause, it's a continuation, a thinner, quieter part of the same timeline. If you could sit in that space, completely alone, you'd still feel your heart beating. You'd still feel the seconds, maybe more slowly, in the absence of sound and warmth. But they'd still come. They always do. And that's why the question of whether the universe knows what time it is remains difficult. Because in a sense it does, just not all at once, not in one voice. Each region, each object, each particle keeps its own time. And in the vast, empty stretches where nothing speaks, time still listens. We'll come back to those stretches again. But now it might be time to ask a different question. If time is part of the structure, even in stillness, then what gives it direction? Why does it feel like it moves forward? You've probably heard time described as a river, flowing forward, carrying everything with it. The metaphor is everywhere, easy to picture, easy to understand. But it doesn't take long to find cracks in that image. Rivers follow gravity. They cut through rock. They meander. They split and rejoin. Time doesn't always seem to do that, at least not in ways we can watch. It doesn't loop back. It doesn't break off and flow in two directions at once. And unlike a river, time doesn't have a landscape to erode. Or does it? Start with the basics. We say time moves forward. We talk about the past being behind us and the future ahead. But physics doesn't require that direction. In fact, most of the laws that govern particles and forces are time-symmetric. That means they work the same way whether time moves forward or backward. The equations don't care. Think of two balls colliding on a pool table. You could watch that in reverse, and it would still make sense. The physics checks out either way. Nothing about the basic rules of motion forces direction. It's just a matter of perspective. So why do we experience time in only one direction? That's not just a philosophical question. It's a physical one, and the answer starts with something called entropy. Entropy is a measure of disorder. Or more precisely, it's a measure of how many ways a system can be arranged while still appearing the same at a broad level. The more disorder, the higher the entropy. A box full of gas molecules moving randomly has higher entropy than the same molecules neatly lined up. A broken egg has more entropy than an unbroken one, and entropy increases over time. That's one of the few truly irreversible processes in nature. It's called the second law of thermodynamics. In a closed system, entropy tends to rise. Things move from order to disorder, not because disorder is stronger, but because there are more ways to be disordered. That's the first real arrow of time, not because something pushes it forward, but because the odds are tilted. There are more future states than past ones, more ways for things to spread out than to gather together, more ways for energy to diffuse than to concentrate. So even though the equations of physics don't care which way time moves, the initial conditions of our universe do. We started with low entropy. That's what sets the direction. That's what gives us a sense of before and after. If you drop a glass, it shatters. You don't see it jump back together. Not because it's impossible, but because it's unbelievably unlikely. It would require all the pieces to move in exactly the right ways at exactly the right time to reverse the process. The laws allow it. But reality doesn't. So time, as we live it, has a direction because entropy increases. It's not about clocks or calendars. It's about the tendency of systems to spread out, to settle, to become more probable. But even that direction isn't absolute. It's just what we see from inside the system, from our place in it. Think about the universe as a whole, a massive, expanding structure filled with particles, fields, and forces. It's not a single river. It's more like a web, each thread shaped by motion, by gravity, by the curvature of space-time. Those threads can run parallel, they can twist, they can stretch apart. Each one carries its own sense of time. That web doesn't require a global direction. It doesn't require a shared clock. Each local system has its own timeline, its own sequence of events, its own increase in entropy. What gives us the sense of a unified direction is just that most systems around us are behaving similarly. They're moving from order to disorder, from past to future, from low entropy to high. But there are exceptions. Quantum systems, for example, can evolve in ways that don't fit neatly into this pattern. In certain conditions, particles can become entangled, linked so that the state of one depends on the state of another, no matter how far apart they are. That entanglement doesn't follow the usual idea of sequence. Measuring one particle seems to affect the other instantly, not because information travels faster than light, but because the two outcomes were part of the same, larger process. In those cases, time doesn't behave like a river. It behaves more like a network. Events aren't lined up one after another. They're connected in a structure, a framework of relationships. And even at larger scales, the metaphor of the river starts to break down. Galaxies aren't moving through time at the same rate. Gravity bends space-time, and that includes time. So some parts of the universe are aging faster than others. Some processes are happening more slowly. Some clocks tick more quickly. The river has eddies, whirlpools, places where the current changes speed or direction depending on local conditions. That's why physicists now think of time less like a flowing substance and more like a geometric property. Something that stretches between events, something you can move through along different paths depending on your motion and your position in the universe. Time, in this view, is one coordinate in a four-dimensional structure. Space gives you 3 dimensions. Time gives you the 4th. Together, they define your location, not just where you are, but when you are. That makes time less of a river and more of a landscape, a field, a web of potential connections. You can move through that field in different ways, accelerate, and your clock slows down. Enter a gravitational well, and it slows again. Take a different path through space-time, and you arrive at the same destination with a different number of seconds behind you. The river metaphor tries to simplify that into one direction, one current. But reality doesn't follow one line, it follows a fabric. That doesn't mean time is unreal, it just means the way we experience it is shaped by our environment. Our brains, our biology, our thermodynamics, all of them push us toward one interpretation of time, one experience. But the deeper structure is more flexible, and that flexibility allows for some strange possibilities. If time is a dimension, then in theory, past and future both exist, just like every location in space exists, even if you're not standing in it. The moment you were born and the moment you die could both be part of the same structure, fixed, mapped, waiting. But you can only move one way through that structure. That's the strange part. Physics allows the full map. But your consciousness, your biology, your memory, all of that flows forward. One moment to the next, one breath to the next. You don't get to rewind, you don't get to skip ahead. You move through the web in one direction, even though the web itself isn't directional. And if the structure is real, if all events exist somewhere in space-time, then what separates the present from the past or future? That's not a settled question. Some physicists believe that only the present is real, that the past is gone and the future hasn't happened. Others argue that all of it is equally real, that the flow of time is a product of perception, not physics. It's not easy to test. You can't step outside of time to examine it. You're inside the structure, trying to describe its shape from within. But what we do know is that time doesn't have to flow like a river. It can bend, it can stretch, it can behave like a network of connections instead of a single path. And in a network, location matters, sequence matters. But direction isn't always fixed. You feel time flowing forward because that's how memory works. That's how cause and effect work. That's how entropy moves. But underneath that, in the math, there's room for more complexity, more variation, more paths. That doesn't change your experience, but it adds context. You're not drifting down one river. You're walking a strand in a much larger web. And every step you take is shaped by the structure around you, by the gravity you feel, the speed you move, the systems you interact with. So when you wonder why time moves forward, you're really asking why the local structure of space-time favors one direction. And the answer, so far, is that it comes from the conditions we started with. A universe that began in low entropy, a structure that allowed complexity to grow, a framework that gives you memory, thought, sequence, history. But it's not universal, not everywhere, not always. And maybe, in some distant corner of the cosmos, conditions are different. Maybe entropy decreases there. Maybe time runs backward from our point of view, not in violation of physics, but in full agreement with it, just following a different path through the web. That idea is hard to grasp, but it's not impossible. It's part of what the math allows, and so we keep it in mind, not as a conclusion, but as a possibility, as part of the strange, flexible shape of time. If time was simple, we wouldn't need to describe it in curves. We talk about it the way we talk about a straight road or a tape measure, just a number, a line, something to follow. But time, it turns out, doesn't behave that way. Not when you look closely, not when you measure carefully. That's where relativity comes in. You don't need to know equations to understand the basic idea. It starts with something intuitive. Not everyone agrees on when things happen. Two people watching the same event from different places or moving at different speeds won't necessarily describe the event the same way. One might say it happened before something else. The other might say it happened after, and both of them can be right. That disagreement isn't just a quirk. It's built into the way the universe works. In the early 1900s, Einstein put this into mathematical form. He took two things people assumed were separate, space and time, and showed they were actually parts of the same thing, space-time. That sounds abstract, but the consequences are real. Because if space and time are connected, then stretching one stretches the other. Bending one bends the other. They don't exist in isolation. Relativity showed that time is not absolute. It's not a fixed background that events play out against. It's a dynamic part of the world. It responds to speed. It responds to gravity. And in both cases it curves. The simplest version is called special relativity. It deals with motion. When you move quickly, especially near the speed of light, time slows down for you compared to someone who stays still. Not because your clock is broken, but because your entire experience of time changes. You age more slowly. Your process is slow. Your seconds stretch out. This isn't a theory that just lives on paper. We've tested it. Particle accelerators show us that unstable particles live longer when they're moving quickly. They decay more slowly, not because the particles know they're moving, but because time itself is dilated. Their internal clocks tick at a different rate. Even astronauts experience this. When someone spends time aboard the International Space Station, orbiting Earth at high speed, they age slightly less than someone who stayed on the ground. The difference is tiny, fractions of a second, but it's measurable. That's special relativity. Speed affects time. Then there's general relativity. It goes further. It says gravity, too, affects time. And that's where the curves come in. Imagine space-time as a fabric, a surface stretched flat in every direction. If you put a heavy object on that fabric, a planet, a star, anything with mass, it sinks in slightly. It creates a depression, a curve, and that curve changes how things move nearby. This is gravity, not as a pull, but as a shape. Planets orbit stars not because they're being tugged by an invisible force, but because they're following the straightest possible paths through a curved space-time. Those paths look like orbits because the fabric they're moving through isn't flat. But here's the twist. That curve doesn't just affect space, it affects time too. The deeper you go into a gravitational well, like closer to Earth's surface, the slower time runs. If you stand on a mountain, time moves a little faster for you than it does for someone at sea level. Again, the difference is small, but it's there. Atomic clocks confirm it. And in stronger gravity, the effect becomes much more dramatic. Near a black hole, the curve is so deep that time practically stops at the edge. From far away, anything falling in appears frozen at the event horizon, not because it's actually stopped, but because the light carrying information about its motion is stretched out, slowed down, smeared over an ever longer time frame. That's gravitational time dilation. And it's not optional, it happens automatically, as part of the geometry of space-time. So now we have two ways time can curve, through motion, through gravity. And those curves aren't rare, they're everywhere. Even your own body creates a tiny dent in space-time. So does the chair you're sitting in, so does every object with mass. The dents are minuscule, but they're real. They're part of the full structure of the universe. Every curve changes the local experience of time, however slightly. That's what makes relativity so different from our everyday experience. It tells us that time is not a universal tick. It's a flexible dimension shaped by everything around it. And when you stack those curves together, mass and motion, acceleration and velocity, you get even more complex patterns. Time might run more slowly in one place and more quickly in another. The differences might be small, or they might be extreme, but they're not errors, they're baked into the system. One way to picture this is to think of a map. On a flat map, every inch is equal. But on a globe, distances curve. The shortest path between 2 points isn't a straight line on the map, it's an arc on the surface. Time works the same way in curved space-time. The path between two events isn't always what you'd expect. It depends on the geometry, and that geometry isn't fixed. It changes as mass moves, as energy flows. The shape of space-time is dynamic. It evolves, which means time evolves with it. This becomes especially important when we think about the early universe. Right after the Big Bang, everything was compressed into an incredibly hot, dense state. The curvature of space-time was extreme. That means time behaved very differently then than it does now. It wasn't just faster or slower, it followed different rules, different constraints. As the universe expanded, the geometry changed and so did time. That's part of why understanding the early universe is so hard. We can't just rewind the clock. We have to account for the fact that the clock itself was changing. Not only what time it was, but how time worked at all. The same applies in the future. As the universe continues to expand, possibly accelerating, space-time stretches. Galaxies move farther apart, the fabric thins, the curves flatten. That has implications for time too. Far from gravity, in the deep future, time may flow differently again. Not because of some outside influence, but because the structure allows it. So when we say time is curved, we're not using a metaphor. We're describing how it behaves in the presence of mass and motion. We're explaining why clocks don't always agree, why simultaneity breaks down, why the answer to what time is it depends entirely on where you're asking from, and that raises a question we'll keep coming back to. If time is shaped by the curves of space, then what happens where those curves become extreme? What happens where space-time itself breaks down? That's where we begin to approach the edge of what we know. Black holes, singularities, the very beginning of the universe. Places where the curvature becomes so sharp the math stops working, where our models collapse, where time might stop altogether or cease to mean anything at all. We'll move to all those places soon. But before we do, it's worth remembering that the curves of time aren't just out there. They're here too. Every clock you've ever seen, on your wall, on your wrist, in your phone, is following its own path through curved space-time. Your body, your thoughts, your experiences, all of them shaped by where you are, how you move, what's nearby. You live in time, but you also shape it, just by existing in the fabric. That's not a poetic idea, it's a physical one. Relativity makes it clear. Time with curves is the only time there is, so when we keep asking whether the universe knows what time it is, we have to be precise. Where in the universe? For whom? Under what conditions? Because there is no single answer. There is only time shaped by the curves it travels through. We'll trace those curves further next, especially the sharp ones. You can trace time backward in a lot of ways. Personal memory, written history, ice cores, fossil layers, the motion of planets, the decay of atoms. At each step, the record gets thinner, the signals fainter. But the timeline holds. Physics lets us keep rewinding. Go far enough back and you're no longer just looking at ancient events. You're approaching the limits of time itself, not because we run out of data, but because we run into something stranger, a question about whether time had a beginning at all. That idea feels unnatural at first. We're used to everything having a before. If a tree falls, there was a moment before it hit the ground. If a star explodes, there was a time when it hadn't yet begun. But what about time itself? If time began, what was before that? The answer might be that the question doesn't work. Our minds are built around cause and effect, around sequences, around time moving forward. We use that structure to think. But when you ask what came before time, you're using a time-based concept, before, to talk about a place where time might not have existed. It's like asking what's north of the North Pole. You can say the words, but the concept doesn't hold. According to our best current models, the universe has a measurable age, around 13.8 billion years. That age isn't a guess. It comes from multiple lines of observation. The expansion of galaxies, the cooling of the cosmic microwave background, the relative abundances of light elements. They all point to a moment when everything was compressed into a hotter, denser, simpler state. We call that moment the Big Bang. But it's important to understand what that word means, and what it doesn't. The Big Bang wasn't an explosion in space. It wasn't a burst that happened at a point and spread outward into empty surroundings. It was the rapid expansion of space itself, not in space, but of space. There was no outside to expand into. There was no center. Every point in the universe was, at one time, compressed into a much smaller, much hotter region. And from that state, the universe began to expand. If you run the expansion backward, the math takes you to a point of infinite density and temperature, a singularity. But that's not a physical place. It's a breakdown in the equations, a place where our current models stop being useful. We don't know exactly what happened at that point, but most physicists believe the singularity isn't real in the literal sense. It just marks the edge of where general relativity applies. Beyond that edge, we need quantum gravity, a theory that doesn't yet fully exist. Even so, general relativity does give us a starting line, a boundary, a lowest point on the timeline, not a place, but a moment. According to the current picture, time itself began at the Big Bang. There was no before in the sense we understand it, because time, as a dimension, as a physical property, didn't exist yet. That's a difficult idea to grasp, because we're trying to imagine a condition without time while still using time-based language to think about it. It creates a kind of conceptual glitch. You want to ask what caused the Big Bang, or what came before, but if time began there, causality as we know it breaks down. The chain of events doesn't extend any further back, not because something is hidden, but because back stops being a meaningful direction. This is where different theories begin to explore alternatives. Some suggest that time, like space, is curved, that the beginning of the universe is more like the South Pole, a smooth boundary, not a sharp edge. In that case, time might not have a beginning point so much as a round start, a finite past but without a before. Others propose that time is emergent, that before the Big Bang, time as we know it didn't exist, but some other, more fundamental process did. In this view, time is a result, not a foundation. It arises from the behavior of quantum fields or informational structures. If that's true, then asking what happened before time is like asking what's south of a two-dimensional drawing. The question simply doesn't apply. There are also cosmological models that include a bounce. In these, a previous universe collapsed, reached a minimum size, and then rebounded into expansion. Our universe, in this picture, is one phase in a longer cycle. Time didn't begin, it just turned a corner. Some versions of this idea suggest the bounce was smooth, like a compressed spring releasing. Others suggest a more quantum process, where the collapse reached a critical threshold and a new expansion tunnel opened, a kind of universe-level reboot. In those cases, there is a before, but it might look nothing like what we recognize. It wouldn't be a place with stars or galaxies. It might not have had dimensions like ours. It might not have had time that flowed in a direction we'd recognize. Or it might not have been before at all, but rather a different part of the same structure. That's a difficult idea to test. Right now, we don't have the tools to directly observe anything before the cosmic microwave background, the afterglow of the early universe. That light has been stretched and cooled by billions of years of expansion, but it still carries information about conditions a few 100,000 years after the Big Bang. Earlier than that, the universe was opaque, too hot and dense for light to travel freely. We can model earlier phases using physics, but as we push closer to the Big Bang itself, our equations lose confidence. We're operating near, or even beyond, the edge of what general relativity can describe. That's where quantum gravity would come in, a theory that combines general relativity's understanding of gravity and space-time with quantum mechanics' description of the very small. Right now, several candidates exist: string theory, loop quantum gravity, causal dynamical triangulations, but none are confirmed. What they all agree on is that time at that level behaves very differently than what we experience. It might not be continuous. It might not be directional. It might not even be fundamental. It might be statistical, or probabilistic, or derived from something deeper. If that's true, then our everyday idea of a timeline, a sequence of moments stretching from past to future, is just a useful approximation. A higher-level behavior that emerges once the universe has enough structure to support it. In that case, asking where does time begin becomes less about a moment and more about a threshold, a point where the conditions allow time to exist in a way we recognize. Before that threshold, something else was happening, just not something we can yet define. And even if time does have a beginning, that doesn't mean it's a beginning in the way we're used to. It might not have had a cause. It might not have happened at a location. It might not have started from rest. It might simply be a property that emerged when certain relationships took shape. In physics, properties like temperature and pressure don't exist without systems, without molecules moving, without interactions. Maybe time is like that. Maybe the early universe didn't start in time. Maybe it started into time. This perspective doesn't make the question less important. It makes it more precise. Instead of asking what was before time, we start asking what conditions allow time to emerge, or what do we mean by a beginning when there's no time to measure it against? And as strange as those questions sound, they point us toward the edge of what we can know. Not an ending, not a wall, just a frontier. A place where the map fades and the possibilities multiply. It's possible we'll never know what, if anything, came before time. But that doesn't make the search meaningless. Every step closer teaches us something. Not just about the universe, but about what time really is. Not just a series of moments, not just a background, but a structure that responds to motion, to mass, to entropy, to the very act of observation. We're living inside that structure, shaped by it, moving through it, and whether time began somewhere or emerged from something else, it brought us here. You don't usually think much about a second. It's small, it passes unnoticed. But the first second of the universe wasn't like the others. It wasn't quiet, it wasn't simple, it was packed, dense, hot, unstable, and everything that followed started there. That first second is where the structure of the universe took form, not the galaxies or stars, not yet, but the rules, the particles, the forces, the interactions that would shape everything after. To understand what happened during that second, you have to slow it down, split it into pieces, because the events didn't unfold evenly. The earliest changes happened almost too fast to describe. The clock didn't tick, it exploded forward. Start at the beginning. Not before time, but right at the edge where time becomes possible. At time zero, or as close as physics can take us, the universe wasn't a point in space. It was space. It wasn't inside anything, it was everything. A state of extreme temperature, extreme density, extreme compression. The laws of physics as we know them hadn't fully emerged, but energy was there. Pressure, expansion. We don't know what triggered the expansion. We don't know what, if anything, it expanded from. But from the moment expansion began, time had meaning. Events could be ordered. Cause and effect could unfold, and very quickly they did. In the first tiny slice of a second, less than a trillionth of a second, something dramatic happened. Inflation. Inflation wasn't just expansion, it was exponential expansion, a sudden, rapid stretching of space itself. During this brief moment, the universe grew by an enormous factor, many orders of magnitude, far faster than the speed of light. That doesn't violate physics, because it wasn't matter moving through space, it was space itself expanding. No object broke the speed limit, but distances between points grew at an astonishing rate. Inflation explains a lot. Why the universe looks smooth on large scales, why distant regions appear to have started with similar conditions. Without inflation, those regions could never have exchanged information. They'd be too far apart. But inflation stretched out a small, uniform region into the vast space we see today. And then, just as quickly, inflation stopped. That transition released energy, a lot of it, and that energy reheated the universe, filling it with particles, radiation, and heat. This marks the beginning of what we call the Hot Big Bang. From there, the clock keeps moving. Not slowly, but fast enough that each microsecond matters. In the first 100,000th of a second, the universe is a sea of particles. Quarks, gluons, electrons, neutrinos, photons. No atoms, no protons or neutrons yet, just a plasma, a soup of energy and fundamental particles colliding constantly, forming and unforming. The four fundamental forces begin to separate. First gravity, distinct from the others almost immediately. Then the strong force, which will eventually hold nuclei together. Then the electroweak force splits into electromagnetism and the weak nuclear force. These transitions don't just divide forces, they shape how particles behave. What can form, what can decay, which paths become possible. As the universe expands, it cools, and cooling changes everything. By about 1 microsecond after the beginning, quarks begin to combine into protons and neutrons. These are the building blocks of atomic nuclei, stable, but still part of the larger soup. The universe is still unimaginably hot, more than 1 trillion degrees Kelvin. But it's no longer uniform energy. It has structure. It has matter. By the end of the first millisecond, the basic ingredients of atoms are in place. Not the atoms themselves, those won't form for a while, but the components are here. The universe now contains the seeds of everything that will come. During this phase, neutrinos decouple. They stop interacting with matter and begin to move freely through space. They'll keep traveling, barely interacting, for billions of years. Some of the neutrinos from this moment are still moving through you right now, undetected. Slightly later, antimatter begins to vanish. At first, the universe contains equal amounts of matter and antimatter, but they annihilate when they meet, turning into energy. For every billion pairs that cancel out, 1 extra particle of matter is left over. That small imbalance is what allows anything to exist today. We don't yet know why the imbalance occurred. The laws of physics seem to treat matter and antimatter symmetrically, but something broke the symmetry early on. That slight favoring of matter over antimatter, by just 1 in a billion, is why you and stars and galaxies exist. That asymmetry is one of the unsolved problems in physics. We can describe what happened, but not yet why. By about 1 second after the beginning, the The universe has cooled to about 10 billion degrees, still hotter than the core of any star, but cool enough for nuclear reactions to begin. Neutrons and protons start to bind together. The first atomic nuclei begin to form, mostly hydrogen and helium, with trace amounts of lithium, but the electrons are still moving freely. The universe is still a plasma. Light can't travel far without scattering. It'll take hundreds of thousands of years before neutral atoms form, before light can move freely and the universe becomes transparent. But the first second has laid all the groundwork. All the matter that forms galaxies, stars, and planets is already here. The laws that govern energy and motion are in place. The temperature has dropped from near infinity to a level where chemistry and structure will eventually become possible. And time is fully operational. Events proceed. Interactions unfold. There's now a clear direction, from more energy to less, from more symmetry to less, from a smooth state to one with structure. That's the first second. Everything after it is elaboration. Galaxies won't form for hundreds of millions of years. Stars will take even longer. But those processes are slow, predictable, shaped by gravity pulling matter together, one clump at a time. The first second was different. It was fast, wild, dense with changes, packed with transformation. The kind of moment you can't rewind or repeat. Because it didn't just start a sequence, it set the rules. Physics as we know it begins here, not in its final form, but in form stable enough to evolve. We still don't know everything about this moment. We can't observe it directly, but we can infer it through models, through cosmic background radiation, through particle physics experiments that recreate similar energies, and every year those models become more precise. We simulate the particle interactions. We run accelerators to test early universe conditions. We study the patterns in the distribution of galaxies to trace the earliest density variations. And all of it points back to a universe that was once small, hot, dense, and changing fast. The first second didn't contain everything, but it contained enough. Enough for time to matter, enough for matter to survive, enough for gravity to start its slow, deliberate work. And once the moment passed, it didn't repeat. The universe expanded, it cooled, it aged, it became what we see now. But that second is still with us. The ratios of hydrogen and helium, the presence of neutrinos, the imbalance of matter and antimatter, all of them are echoes of that time, and they haven't changed. Even as the universe has stretched and evolved, the imprint of that beginning remains. We live in its aftermath. We build models in its shadow, and we keep trying to understand how so much could happen in so little time. Now we look forward again, not just into the long cooling that followed, but toward the question that always returns. If the universe had a first second, does it have a last? And if so, what does that ending look like? Up to now, everything we've explored has been about how time behaves, where it came from, how it stretches, how it responds to gravity, motion, mass. But all of that still doesn't explain something more basic, maybe even more personal. Why does time move forward? That's not a casual observation. It's a fact of experience. You remember the past, but not the future. You age in one direction. You see causes come before effects. You walk into a room, and you don't expect to find yourself suddenly back in bed from the day before. Your glass can fall and break, but not reassemble and leap back to your hand. These aren't just habits of expectation. They're deeply consistent features of the universe as you know it. This direction, this one-way path, is called the arrow of time. Physics, as we understand it, doesn't demand such a direction. Almost all the fundamental laws are time-symmetric. You can run them forward or backward and get valid results. Newton's laws work either way. Electromagnetism doesn't care. Even quantum mechanics, strange as it is, has time-symmetric versions. The math allows backward motion, but we don't see it. Instead, we experience time as irreversible. And this mismatch between the symmetry of the equations and the asymmetry of lived reality is one of the central puzzles in modern physics. The most widely accepted explanation for this arrow comes from thermodynamics, specifically from the second law. In a closed system, entropy increases. That's not a philosophical idea, it's a statistical one. Entropy measures how disordered a system is, but disorder doesn't mean chaos in the everyday sense. It means how many ways a system can be arranged without changing its large-scale properties. For example, if you have a neat pile of sand grains, that's low entropy. Spread them randomly across a floor, and the entropy is higher. There are far more ways for them to be scattered than neatly stacked. So when a disturbance happens, you're far more likely to end up with a mess. Same with your desk, or your kitchen, or the molecules in a gas. Systems move towards states with more available configurations, and that's not because of some preference or force. It's just math. There are more disordered states than ordered ones, so if left alone, systems naturally slide in that direction. This is what gives time a direction. You can't watch the air in your room suddenly compress into one corner. That's not because the laws of motion forbid it, but because it's so statistically unlikely it might as well be impossible. The particles would all have to move just right, and there's no reason for that to happen. Entropy is what makes broken eggs stay broken, is why memories go one way, why you age but don't de-age. Because every process that unfolds naturally, without external guidance, tends to increase the total entropy. That's the rule. But now there's a deeper problem. If entropy is always increasing, then it must have been lower in the past. Much lower. That's true in your house, in your body, in your city, in the planet, and ultimately in the universe. So why was the universe's entropy so low to begin with? That's the real source of the arrow. Not the laws themselves, but the initial conditions. The universe started in a highly ordered state. Dense, uniform, smooth. The early universe was full of energy, but not complexity. Not yet. As it expanded, it cooled, and structure began to form. Galaxies, stars, planets, life. Paradoxically, those things are made possible by increasing entropy. The universe became more structured in small areas, even as the total entropy increased. But why did it start out so ordered in the first place? No one knows for sure. And that's where the mystery lives now. Because you could imagine a universe that began in a disordered state. Chaotic, high entropy. But that wouldn't give you a clean arrow of time. You wouldn't have a direction to follow. You wouldn't have processes that settle down. You'd have equilibrium from the start. Instead, the real universe began far from equilibrium. And that gave it room to move, to change, to unfold in a particular direction. That's what makes time seem to flow. Not because something pushes it, but because the universe had a place to go. Still, that leaves other questions. Does the arrow of time point in the same direction everywhere? On large scales, yes. Galaxies move apart. Radiation spreads. Stars burn their fuel and don't unburn it. The entropy of the whole system rises. But what about smaller or more exotic places? Inside black holes, for example, entropy still increases, but we can't watch it. From outside, information appears to be lost, though theory suggests it isn't. Time there is warped, curved, hard to follow. Does the arrow hold? Or consider quantum mechanics. In certain interpretations, time doesn't really flow at all. Everything that can happen does happen, in overlapping probabilities. The wave function evolves smoothly, but it only chooses a result when observed. Before that, the system contains all possibilities. Measurement makes one outcome real. But when exactly does that happen? Different interpretations give different answers. Some say the observer's consciousness plays a role. Others say decoherence, interaction with the environment, settles the outcome. Some go further and say nothing really collapses. All outcomes continue in separate branches of reality. In that case, the arrow of time is linked not just to entropy, but to information. What's accessible, what's observed, what's entangled with the rest of the universe. And that brings us back to memory. You remember the past not because it's real in some special way, but because the information about it is preserved, stored in your brain, in your surroundings, in the arrangement of matter. The future hasn't happened, so the information doesn't exist yet, that's the difference. Information flows in the same direction as entropy. As more particles interact, more records form, more possibilities collapse. You leave footprints in the snow, but only after you walk through. This makes the arrow of time something that emerges not just from the universe's beginning, but from the accumulation of effects. Each moment writes to the next. Each change leaves a mark, and those marks only go one way. Could the arrow ever reverse? In theory, maybe. In very special conditions, it's possible to define systems where entropy decreases, but they'd be artificial, carefully prepared, isolated from everything else. The moment you connect them to the wider universe, they fall back in line. Some speculative cosmological models imagine a future where the universe contracts, gravity eventually halting expansion, pulling everything back. In that case, would time reverse? Would entropy decrease as space shrinks? Not likely. Most physicists think entropy would continue to rise, even during contraction. The arrow would still point forward. There'd be no clean reversal, but again, that depends on how things end. If the universe expands forever, entropy will increase until there's no more useful energy. Stars will burn out. Matter will decay. Black holes will evaporate. That's called the heat death scenario. No change, no structure, no memory. A uniform fog, maximum entropy. No more arrow. Not because it's gone, but because there's nowhere left for it to go. That's the quiet end. Not a crash, not a collapse, just stillness. Not because time stops, but because change does. If that's the future, then the arrow of time is temporary. A phase, a feature of a universe that began low and is moving toward high. A brief slope between two plateaus, but we're not at the end, not close. Right now, entropy is still rising, stars are still burning, thought is still forming, the arrow still points forward, and we're riding it. You age forward, you remember backward, and everything you do, every breath, every decision, happens in the context of that direction. It's not a property of time by itself, it's a property of the conditions that time is moving through. That means the arrow isn't fixed into the geometry of the universe. It's woven into the process of change, into heat moving from hot to cold, into particles colliding, into memories forming, into systems settling. That's where we are, a universe still settling, still forming new complexity, still moving from the structure of the early seconds into the deep randomness of whatever lies ahead. The arrow points forward, but that direction only exists because the conditions let it. Entropy doesn't come with sound. It doesn't announce itself. It's not something you hear or feel directly, but it's always there, in the background, beneath everything. Not just a law, but a quiet rule that guides the shape of time. It doesn't push or pull, it allows. The universe began in a state of low entropy. Smooth, uniform, hot, and ever since, entropy has been rising. Not in fits or jumps, but gradually, unstoppably. In every interaction, every transformation, every shift from one state to another, the balance tilts a little more. It's not chaos, it's probability. The number of possible configurations grows, and with it, the likelihood that the system moves toward them. You pour cream into coffee, it swirls and mixes. You don't see it separate again. Not because it can't, but because the mixed state is so much more probable. The same logic applies to everything, everywhere. To gas molecules in a room, to heat spreading through metal, to the orbit of stars in a galaxy. Once energy spreads out, it doesn't come back together on its own. That's entropy. And the second law of thermodynamics says it always increases. Always is a strong word, but in practice it holds. It's what gives time its direction, as we've seen, but it also hints at where time is heading. Because if entropy keeps rising, there's an end point. Not a wall, but a state. A condition the universe leans toward where no more useful energy remains, no temperature differences to drive motion, no fuel to burn, no systems left to break down. That state is often called the heat death. It's not an explosion or a collapse. It's more like a quiet leveling, a fade. Not the dramatic kind, not sudden, slow, gradual, gentle. Right now, the universe is still rich with energy. Stars shine, black holes grow, planets radiate heat into space. But that energy is being used up, not destroyed, just converted into forms that can't do useful work. Every time energy moves from a hot place to a cold one, entropy increases. That's true whether it's a cup cooling on a table or a star radiating into space. The flow moves in one direction, always outward, and eventually that flow evens out. Over vast stretches of time, far longer than the current age of the universe, stars will exhaust their fuel. Some will explode, some will collapse, some will fade into cold, dark remnants, white dwarfs, neutron stars, black holes. The bright phase of the universe is temporary. The galaxies that glow today will dim, one by one, cluster by cluster. But even that doesn't mark the end. Those remnants, dense, inert, will remain, and they'll continue to cool. They'll give off radiation, slowly, into the ever-expanding void. The expansion matters. As space stretches, energy spreads thinner. The background temperature drops. The night becomes colder, not just in perception, but in measurable degrees. Eventually, only black holes will remain. And even they won't last forever. According to Hawking radiation, black holes emit particles, not many, not quickly, but steadily. Over vast timescales, this process causes them to shrink. The larger the black hole, the slower the evaporation, but given enough time, even the most massive ones will disappear. When the last black hole evaporates, the universe will be left with a thin soup of particles, low energy, high entropy, no structure, no difference. That's what the heat death means. Not fire, not ice, just balance. Nothing left to change, nothing left to interact. Not because time stops, but because time no longer has anything to act on. We call this the end, but it's not a single moment. It's a slow transition, stretched over countless trillions of years, a fade in which everything interesting, everything with contrast, with motion, with memory, gradually settles into stillness. That's where entropy points. Not because the universe wants it. There's no desire here, just math, just probability. More configurations are disordered than ordered. More pathways lead away from structure than toward it. So over time, that's the direction things go. Some people find that idea unsettling. A universe with no outcome, no finale, just an endless drift into thermodynamic silence. But from another angle, it's not an end, it's a result. The final form of a system that started far from equilibrium and had time, so much time, to evolve. And that's what entropy is really about. Evolution in a broad physical sense. From simplicity to complexity to stillness. From potential to outcome. Along the way, entropy makes life possible, not just in spite of it, but because of it. Your body increases entropy. Every breath, every heartbeat, every thought. You eat low-entropy food and convert it into motion, heat, structure, waste. You're a local pocket of order in a universe of rising disorder, and that's allowed, not forbidden, by the laws of thermodynamics, because your order comes at a cost. Your surroundings become more disordered than you become ordered, and that imbalance keeps the system consistent. The same applies to all structure. Stars form by compressing gas. That decreases local entropy, but increases it overall through radiation, turbulence, collapse. The balance always holds, always rising in total. So the universe doesn't move from order to disorder in a simple straight line. It moves from low entropy to high, but that path includes patterns, spirals, cells, mines. Because those structures are efficient at spreading energy, at accelerating the increase in entropy. Life exists not in defiance of the second law, but as a partner to it. And that helps make the gentle fade feel less like a failure and more like a continuation, a long slope, one that includes everything, every system, every memory, every rise and fall. Entropy is the measure of how far we've traveled from simplicity, and it keeps climbing. The further it climbs, the fewer changes remain, but we're not near the end. Right now, stars still shine, clocks still tick, thought still happens, and entropy still rises. The arrow of time is sharp, the slope is steep, the future remains full of motion. But we know where the slope leads. It leads to flatness, to equilibrium, to no more imbalance. And when that happens, the fade will be complete. Not silent necessarily, but quiet. Still moving, in the most technical sense, but with nothing left to distinguish moment from moment. That's what entropy points to. It's not a judgment, it's a pattern. A pattern that began when the universe began, and that continues with every passing moment. We're part of that pattern. Every breath, every flicker of thought, every decision, every system we build, all of them push a little more energy into places where it becomes less useful. And all of them mark time, not with ticking, but with change. Even memory is part of entropy. It's a trace, a mark left by a process. And once enough processes have run, there's nothing left to record, nothing left to mark. But we're not close. There's still plenty to happen. Plenty of time for stars to form and die, for civilizations to rise and vanish, for galaxies to drift and dissolve, for everything that can happen within a long, fading slope to play itself out. The fade is real, but it's not a drop. It's just the tail of a very long process. We usually know time by change, a second hand clicking forward, a sun moving across the sky, a body aging, a thought finishing. We don't just measure time with clocks, we feel it through difference, through motion, through contrast. But what happens when change slows down? What happens when the things that used to mark time, the turning of planets, the fusion inside stars, the drift of heat from one place to another fade into stillness? Would time still pass if nothing is there to tick? Right now, the universe is still busy. There are trillions of stars burning hydrogen into helium. Galaxies collide. Radiation pulses through space. There are particles interacting, decaying, pushing, responding. Every one of those changes is measurable. Every one of them slices time into pieces. Something has changed, so we say time has passed. But in the far future, those changes become rare. We talked about heat death, a state where entropy reaches a maximum and useful energy runs out. But that state isn't just cold and quiet. It's empty of contrasts. With no stars burning, no planets orbiting, no matter clumping together or falling apart, the physical events that once gave us a rhythm are gone. That doesn't mean time has stopped. It means time has nothing left to measure. And that's a different kind of question. We tend to think of time as something separate from events, a background, a flowing dimension that things happen in. But in modern physics, especially in relativity and quantum mechanics, that picture doesn't hold. Time isn't a passive stage. It's tied to the processes that occur. It's defined by relationships between events. This leads to a strange possibility. Maybe time doesn't exist independently. Maybe it only makes sense when things are happening. It sounds philosophical, but the physics is serious. In relativity, you don't have an absolute time. You have space-time, a structure that includes both space and time shaped by mass and energy. Clocks don't tick universally. They tick locally, depending on speed and gravity. That means time is not something that exists on its own. It's something that emerges from the behavior of matter and energy. In quantum mechanics, things get stranger. There are interpretations in which time doesn't even appear as a fundamental quantity. Instead, the system evolves relative to other parts of the system. Time is what we assign when we compare changes in one variable to another. In these views, time isn't a thing. It's a label for relationships. This electron's spin compared to this photon's path. This atom's vibration compared to this field's amplitude. If nothing changes, if all systems become static, then there's nothing to compare. No before, no after, no tick. That leads to a disturbing but meaningful conclusion. In a perfectly static universe, time might still exist mathematically, but it would be meaningless physically. Imagine a perfectly frozen room. Nothing moves, no particles drift, no atoms vibrate. There's no decay, no light, no temperature differences, no memory. You could say time is passing, but by what evidence? From whose perspective? Without a process, there's nothing to measure. You wouldn't just lack motion, you'd lack the possibility of motion. And without that, time becomes something you can define on paper, but not observe in the world. This matters as we look toward the end of everything. As entropy increases, usable energy decreases, processes slow. First it's the stars, then the slow gravitational collapses, then the black holes, evaporating over unimaginable time spans. But after that, after the last evaporation, what's left? A thin, uniform spread of extremely low-energy particles, mostly photons, maybe some neutrinos, maybe some dark matter, spreading apart forever in an expanding space. If nothing interacts, if no new structures form, if no patterns emerge, then there's nothing left to tell time by. There's still a timeline, you can label coordinates, but there's no motion, no sequence, no clocks, and so time loses its meaning. This is what some physicists mean when they say time could end. They don't mean it disappears like a snapped string. They mean it fades into irrelevance, like a measuring stick in a universe with no distances left to measure. The tool still exists, but there's nothing left to use it on. This is where the idea of a ticker becomes important. A ticker is any process that can count. A pendulum, a vibrating atom, a decaying nucleus, a collapsing cloud. You compare change against change. But if all the tickers are gone, time doesn't stop. But it stops being something you can experience. And that's the deepest version of the heat death. Not just cold, not just still, but undifferentiated. A system where nothing happens, and so time, for all practical purposes, no longer ticks. Does that mean time is subjective? Not entirely. It still exists in equations. The universe still has a history. It still has a structure in space-time. But your experience of time, your sense of now, of duration, of sequence, depends on having processes. Without them, time becomes invisible. Not false, but empty. This isn't the same as death. It's not even destruction. It's dilution. Everything that once marked the passage of time spreads out so far and becomes so even that it leaves no difference behind. You can't track a change that never varies. And so you return to the same strange question. If there's no change, is time still real? Some physicists say yes, others say no. Some say the question doesn't even matter, because a universe without change has no observers, no processes, no outcomes. It's not just a silent place. It's a place where the concept of place and when dissolve. But we're not there. We're still surrounded by tickers. The Earth turns, the moon pulls at the ocean, stars shine, galaxies drift. Even now, in your body, in your neurons, in the air around you, there's motion. There are relationships. There is time. And that means we can still ask the question, what would time mean if there were no more clocks? Because when the clocks run out, when the decay ends, when the energy levels bottom out, what you're left with is a structure that no longer carries rhythm. No cycles, no pulses, no changes in state. Just one long, flat drift through a coordinate that no longer registers. Time without a ticker isn't gone, but it's unreachable. And that may be the final phase of time, not a wall, not a stop, just a flat line, stretching endlessly, with nothing left to count. So far, we've looked at time through the lens of large things, stars, galaxies, black holes, the entire universe. But time isn't only a matter of scale. It's also something that shows up in the smallest places imaginable. The world of particles, fields, probabilities, the quantum world. That's where things begin to look different. Not just in the sense of being tiny or fast or strange, but in how time itself is defined, or whether it's defined at all. In classical physics, you can always ask where something is and how fast it's moving. You can draw a clear path. You can assign a time to every point. But in quantum mechanics, particles don't follow neat trajectories. They exist in a spread of possibilities, clouds of potential outcomes. They aren't here or there. They are likely to be here or there, and that likelihood doesn't stay fixed. It shifts, it evolves. But how do you talk about time in a world where things don't move in the usual sense? In quantum mechanics, time is a parameter, something you plug into the equation to watch the system evolve. You don't measure time directly. You observe how probabilities change as if time is passing. That's a subtle but important distinction. Take the Schrödinger equation. It governs how the wave function of a quantum system changes over time. But it doesn't say what time is. It assumes time exists, then uses it to describe change. The structure depends on time, but doesn't explain it. This becomes even more curious when you ask what a clock looks like at quantum scales. You might imagine some kind of atomic transition or a vibrating particle, and we do build atomic clocks using that principle, comparing the frequency of electromagnetic radiation emitted by atoms as they change energy states. But the concept of a clock breaks down as you go smaller. A quantum system doesn't keep time in the classical sense. It exists in superposition, multiple states at once, and it only chooses a result when it interacts with something, when it's measured. Before that, it doesn't tick, it floats. That gives us a problem. If the smallest pieces of reality don't follow a clear timeline, what does that say about time as a whole? Some physicists argue that time is not a fundamental property of the universe. Instead, it's emergent, a statistical result of many quantum systems interacting. Just like temperature doesn't make sense for a single molecule, but becomes meaningful for a group, maybe time arises only when enough particles are involved. Others go further. There are theories in which the universe is timeless at its core. The fundamental laws don't describe change. They describe relationships, and change, what we experience as time, comes from comparing those relationships. The idea is called the problem of time in quantum gravity, and it's one of the biggest unresolved questions in theoretical physics. When you try to combine quantum mechanics with general relativity, when you try to build a theory of everything, time gets in the way. The usual version of time doesn't appear naturally in many of the proposed equations. It has to be put back in, through approximations or assumptions. And this leads to something even stranger. If time doesn't exist fundamentally, then why do we experience it so consistently? One answer might be that time is what happens when large numbers of quantum systems become entangled. When particles interact with their environment, their possible states collapse into outcomes. That's decoherence. It's what gives you a definite result, and it might be what gives rise to the feeling of sequence. Every interaction writes a bit of history. Every measurement marks a then. The more complex the system, the more these records accumulate. Eventually, they pile up into something like a timeline. So maybe time isn't real at the deepest level. Maybe it's a bookkeeping trick, a way to describe patterns in how probabilities evolve as systems grow more complex. Still, even if time isn't fundamental, quantum systems still change. They still have dynamics. The wave function still evolves. And in some sense, those changes are the tiniest ticks of the universe. But they're not smooth ticks. They jitter. They flicker between states. They jump when observed. The path from one result to another is not a smooth curve. It's a probability cloud suddenly made definite by measurement. That jitter isn't noise. It's reality. In quantum field theory, even empty space isn't empty. It's alive with fluctuations, fields vibrating, particles appearing and vanishing. The vacuum is full of motion, even at zero temperature. That's what gives us the Casimir effect. That's what contributes to dark energy. And that's what tells us, even in what looks like stillness, the quantum world doesn't stop moving. And if time means anything here, it's tied to those fluctuations. Maybe the jitter is the real tick, not the swing of a pendulum, but the flicker of probabilities adjusting themselves with every interaction. You don't see it directly, but it's there. It's in radioactive decay. A single atom has no clock inside it telling it when to decay. It happens unpredictably, even though the half-life of a group is well defined. That randomness is quantum jitter. It doesn't violate causality. It's just fundamentally probabilistic. You see it again in quantum tunneling. A particle facing a barrier might not have enough energy to climb over it, but there's a probability it will appear on the other side, not because it broke a rule, but because the wave function includes outcomes where that happens. Even photosynthesis in plants or reactions in your body use quantum effects. Coherence, interference, tunneling. These aren't exotic details. They're fundamental to how matter works, and through all of it, the jitter continues. That makes time messy at small scales. You can't assign a universal now to a quantum system. You can't rewind a measurement. You can't predict exact outcomes, only likelihoods. That's not a limitation of tools, it's a feature of the universe. So when we ask what time looks like in the quantum world, we're not looking for a stopwatch. We're looking at a process that only becomes time-like when many possibilities collapse into one. That collapse doesn't erase the other outcomes, not always. In some interpretations, like many worlds, those outcomes still exist, branching off into their own versions of reality. In others, they vanish completely. But in all cases, time only shows itself at the point of interaction. It's not flowing underneath the system. It's appearing at the moment of measurement, and that forces us to rethink what we mean by before and after. In the quantum world, those labels aren't automatic. They depend on the context, on the observer, on the system, and on what counts as a clock. Maybe time, at that level, is less like a stream and more like a sea of possibilities. Smooth in some areas, choppy in others, flat where no events occur, bubbling where interactions happen. Those bubbles, the little jitters, are what give rise to everything we see. And when enough of them align, when enough systems interact, we get patterns, we get clocks, we get the flow of time we're used to. But under all that, time is jittery, not smooth, not inevitable, just a structure built from comparisons, one state after another, as far down as we can go. And yet, even with all the uncertainty, all the randomness, all the ambiguity, those flickers add up. They accumulate. They generate order. They power change. They mark the smallest ticks. So maybe that's where time begins, not in the fabric of space or the ticking of a mechanical clock, but in the moment a quantum state becomes something definite, when potential becomes history, not with a bang, with a flicker, and as we move on, we'll carry that flicker with us. You don't have to be awake to experience time. You can lie down, close your eyes, and drift into sleep, and still, somehow, time continues. Not as a clock on the wall or the turning of the earth, but as something inside you, a rhythm that persists even when the world is gone. We experience time in dreams. We age inside them. We wait. We move. Things happen in order, sometimes slowly, sometimes impossibly fast. But there's still a sequence, a beginning, a middle, an end, and yet none of it happened physically. So where is that time coming from? The human brain doesn't have a master clock. There's no central metronome ticking off seconds like a machine. Instead, time is built from activity, neural loops, chemical signals, oscillations between regions. You track time by comparing events, by measuring change inside your own system. Even when you sleep, some of these loops keep running. One of the most studied areas is the suprachiasmatic nucleus, deep inside the brain. It's a cluster of about 20,000 neurons that helps maintain circadian rhythm, the rough 24-hour cycle that controls sleep, temperature, hormone release. It doesn't know what time it is in any global sense, but it keeps time internally, adjusting based on light input from the eyes. It's not precise down to the second, but it's enough to anchor your sense of day and night. That's one form of internal time, but there are others. Time perception happens across multiple brain regions. The cerebellum contributes to short intervals, fractions of a second. The basal ganglia, involved in movement and reward, help measure seconds to minutes. The prefrontal cortex handles longer durations, attention, expectation. All of these systems talk to each other. They don't agree on a single now. They each have their own rhythm, their own way of keeping track of change, and because they interact, your sense of time becomes fluid, adaptable, context-sensitive. That's why time feels different depending on what you're doing. When you're bored, time seems to stretch. When you're focused, it contracts. In a crisis, you remember moments in slow motion. During routine, hours vanish. Time perception isn't constant, it's constructed, actively, continuously, and it can change. Dreams are proof of that. When you dream, the world outside fades. Your body doesn't move, your senses don't receive much input, but your brain is still active, sometimes more active than when you're awake, especially during REM sleep when most vivid dreams occur. In REM, brain activity rises in the visual cortex, the emotional centers, the motor regions, but activity drops in the dorsolateral prefrontal cortex, the part responsible for logical reasoning and critical awareness. That's why dreams feel real when you're in them, even if they're strange. The part of your brain that usually checks for consistency is offline, and in that altered state, time continues, not always accurately, not always realistically, but enough to allow sequence, enough to allow memory, enough to allow the feeling of before and after. Some dreams feel like hours but happen in minutes. Others seem short but cover years. Experiments have shown that dreaming brains can keep time relatively accurately for certain tasks. Lucid dreamers, people who know they're dreaming, have been trained to signal with eye movements inside the dream, and researchers have measured the intervals. The results suggest that, at least in some states, dream time maps fairly closely to real time, but not always. Dream time can bend, it can jump, it can loop, and yet the feeling of duration persists. That's because your brain isn't counting seconds. It's constructing a timeline out of events. It's not measuring time. It's experiencing it through change, through memory. And memory is key. Your sense of time depends on how many changes you can recall. If a lot happens, time feels full. If little happens, it feels thin. That's true when you're awake. It's even more pronounced when you dream. Dreams are time without anchors. No clocks, no sun, no schedules, just the unfolding of imagined events. But those events are enough to give time a shape. This tells us something important. Time, as we feel it, is not just about the world outside. It's about internal rhythms, internal records, internal difference. That's why two people in the same moment can feel time so differently. One feels rushed, the other feels calm. One is counting every second, the other is floating. The external clock is the same, but the internal one is personal. It also changes with age. Children experience time differently than adults, partly because everything is new. Novelty makes time feel longer. A single day in a child's life can feel endless because their brain is recording so much. Each experience creates new patterns, new memories. As we age, repetition sets in. Fewer new events, fewer surprises, and the brain compresses similar memories. Days blend, weeks vanish. Time seems to speed up, not because it is, but because the brain is leaving fewer marks. Dreams can sometimes reverse that. They can restore novelty, create strange connections, mix unrelated memories. That's why they can feel long, even when they're brief. They're dense with activity, with difference. And so they remind us that time in the mind is elastic, not fake, not meaningless, just different. That elasticity is one of the brain's survival tools. You don't need perfect timekeeping, you need useful timekeeping. Enough to coordinate, to anticipate, to respond. And when the body rests, the mind doesn't stop. It keeps exploring. Sometimes it replays the day, sometimes it invents, sometimes it sorts. But always it keeps its rhythm. Even when you're unaware, some part of you is keeping time. And that brings us back to the deeper question. If time feels real, even when it's built from dreams and guesses and memories, then what is it really? We've seen that clocks in physics depend on energy, on decay, on systems in motion. But clocks in your mind depend on attention, on emotion, on the density of memory. The two are not the same, but they mirror each other. A radioactive isotope decays at a fixed rate. A neuron fires when a signal crosses a threshold. Both processes have timing, but one is based on fundamental particles, the other on networks and meaning. You live in both systems at once. You're subject to the time of the universe, the orbit of Earth, the flow of entropy, the laws of physics, but you also live inside your own sense of time, the time of breath, of reaction, of expectation. And that internal time doesn't stop when you sleep. It reconfigures. Dreams are the proof. Even in altered states, your brain creates time. Not because it has to, because it needs it. Time, for the mind, is structure. A way to link events. A way to find order in memory. Without time, you can't have cause and effect. You can't have narrative. You can't have meaning. That's why time shows up even when everything else disappears. It's one of the mind's most basic frameworks, a scaffolding that holds everything together. You look up at the moon, and it looks back blankly. Not because it sees you, but because it doesn't see at all. Still, it's there every night, bright and cold, casting light into darkness. You might feel something when you see it. Calm, distance, a kind of rhythm. You might even think, there's the moon, it's night now. But does the moon know it's night? Of course not. The moon doesn't know anything. It doesn't have awareness, no brain, no thought, no language. But the question lingers, not for what it says about the moon, but for what it says about time. We divide our lives into pieces, day and night, morning and evening, this week and last year. We use the sun and the moon as reference points. The rising and setting of light becomes the framework for activity, for rest, for meaning. But the universe doesn't divide time that way. Nature doesn't recognize day or night as categories. Those are human interpretations of light and shadow. The moon doesn't change itself to reflect our idea of nighttime. It reflects sunlight. Half of it is always lit, half is always dark. The side we see depends on angles, not intention. It's not shining for us. It's not announcing anything, and yet we still use it to tell time. For much of human history, the moon was the calendar. Its phases mark the month. Its rising and setting mark the tide. Even now, without clocks, without electricity, you could use the moon to guess what part of the night it is, but the moon doesn't change its behavior based on your attention. That reveals something important. The systems we use to track time, celestial movements, biological rhythms, electronic pulses, don't require our awareness to function. Time, as measured by the motion of the moon, keeps passing whether you watch it or not, whether you care or not. But your awareness still shapes what that time means. You call it night, when the sun is down and the moon is up. You associate it with sleep, with quiet, with dreams, with the end of a cycle. You don't feel the same way at noon. The physical conditions are different, but so is your mental framing. The moon doesn't know it's night, but you do. And that raises the question, what does time mean without a mind to interpret it? This isn't just a poetic musing, it's a real philosophical and scientific problem. Does time exist independently of observers, or is it only meaningful when it's measured, recorded, or remembered? Physicists generally treat time as part of the structure of the universe. Events happen in sequence. One thing follows another. You can plot them on a timeline, measure intervals, compare durations. No observer is needed for the math to hold, but quantum mechanics complicates that view. In some interpretations, a quantum event only becomes definite when it's observed. Until then, it exists in a superposition of possibilities. If you accept that view, then measurement, interaction, observation plays a role in determining what actually happens. That's not the same as saying consciousness controls reality. But it does suggest that observation changes things. Still, the moon doesn't need to be observed to follow its orbit. The Earth's gravity pulls on it. It pulls back. The interaction is governed by physical law, not awareness, and yet, without awareness, there is no night. There's just a position in a cycle, a location in space, a section of orbit. Our labels, our feelings, our experiences, those are layers we place on top of the physical structure. Does that mean they're wrong? Not at all. It means they're ours. They come from being creatures who live in time, who feel time, who rely on patterns to make sense of motion. We attach meaning to intervals. We recognize cycles. The moon becomes more than a rock in space. It becomes a symbol, a clock, a companion. But to the moon, there is no night, no yesterday, no tomorrow, no memory of impact, no thought about orbit. And yet, despite its silence, it plays a role in our entire experience of time. The tides shift, the nights brighten, the months pass, and all of it comes from motion, regular, indifferent, exact. This tells us something deeper. Time is not always something you feel. Sometimes it's something that simply is. You can watch the moon wax and wane and feel change, but you don't have to. The pattern continues whether or not you notice. In that sense, time is two things at once. It is the structure of events, the order of interactions, the background of causality, and it is the experience of passing moments, the awareness of change, the personal sense that one state has turned into another. The first exists with or without minds. The second only arises through perception. That duality is easy to forget. You might think time is a ticking clock, but a clock is a human tool. The tick is an arbitrary slice. You might think a minute is always a minute, but your brain doesn't treat it that way. It stretches, compresses, skips. The moon doesn't know it's night, but you do. And so, night becomes real, not because the universe declares it, but because you live inside a body that responds to darkness, a mind that associates it with rest, a culture that builds meaning around it. So where does that leave time? It leaves it layered. The bottom layer is physical, measurable, universal. The laws of motion, the aging of particles, the drift of galaxies, no interpretation required. The top layer is subjective, felt, remembered. It's how long you think something lasted, how you structure a day, how you remember a year. In between are systems like the moon, reliable, regular, indifferent, but co-opted by awareness, used to build calendars, stories, meanings. The moon becomes a timekeeper, not because it intends to, but because we decided it is. And through that decision, we built a shared structure. Civilizations synchronize their crops, their ceremonies, their sleep, all built on the rhythms of something that doesn't know it's being watched. That's the strange paradox. Time keeps moving whether we look at it or not. But meaningful time, the kind that matters to minds, only exists when we engage with it. So the moon doesn't know it's night, but its position, its cycle, its presence in the sky, all of it gives us the shape of a moment. And sometimes that's enough. Even if the moon isn't aware, we are. And that awareness is what builds the feeling of a timeline. Events, transitions, endings, beginnings. Not because they happen in isolation, but because we notice. You always live in the now. You don't access the past directly. You don't step into the future. All thoughts, actions, sensations, they happen here, this moment, whatever that means. But what is now, really? It feels like a sharp point, something that separates before from after. A thin slice where you exist, where you choose, where you remember or forget. The past is gone, the future isn't here yet, and now is all there is. But that now never stays. You can't hold it. You can't even really locate it. The second you try to pin it down, it's already part of what was. The moment you speak the word now, it's no longer true. So where does it go? Physically, the laws of the universe don't pick out a now. The equations of motion don't care which frame you're in. Whether something happened yesterday or 10 years ago, the math still works. Time appears as a dimension, not a sequence of present moments, but a line, a coordinate. There's no privileged point on that line. In Einstein's theory of relativity, what's now for one observer might not be now for another. Two events that are simultaneous in one frame can happen at different times in another, depending on how fast you're moving. This isn't just a trick of clocks, it's a fundamental part of how space and time behave. There's no single, universal now. Still, subjectively, you always feel like there is. You wake up and you're in the moment. You move through it, one frame at a time. Your memories stretch behind you. Your intentions pull you forward. But everything you actually do, everything you sense or think, happens in a window so small you don't even notice it. Neurologically, the brain doesn't process everything instantly. There's a delay between an event and your conscious awareness of it. A few hundred milliseconds. Your brain gathers input, resolves it, smooths it, and delivers a version of now that's already slightly behind. You're always catching up to yourself. That doesn't mean your experience is fake. It means it's constructed. Just like your sense of color or depth or sound, your sense of the present is something the brain puts together from fragments, and it works well enough, but it's not perfect. In fact, the feeling of now is surprisingly easy to confuse. Think about how fast time seems to pass when you're distracted, or how long a single second can feel when you're waiting for news. Those aren't changes in the external world. They're changes in how your brain passes moments. Even your reaction to simultaneity, where the two things happened at the same time, can shift depending on context. Experiments show that when sound and visual stimuli arrive slightly apart, your brain often adjusts your perception to align them. It creates a coherent version of now, even if it requires bending a few milliseconds. That coherence matters. Your sense of being alive right now isn't based on perfect timing. It's based on continuity, on having a stream of input that seems to follow itself. You feel now not as a dot but as a short interval, a kind of rolling present, not frozen but always updating. Some psychologists call this the specious present, the minimum length of time your brain can process as a single experience. Estimates vary, but it's usually less than a second. That's your working window. That's the scale where perception becomes action, where events are stitched into meaning, and that's what you think of as now. But the boundaries are soft. If you're in danger, your sense of time contracts, you react faster. The window narrows. If you're calm, it expands. The moment stretches. You don't control this consciously. It's baked into how you function. That's why now feels so different depending on what you're doing. The brain needs a present to survive, to act, to learn. But that present is never perfectly sharp. It's always smeared slightly across time, always being revised. That smearing leads to interesting consequences. In some cases, the brain reorders events to make sense of them. You touch a surface and feel heat, and your brain synchronizes the tactile and temperature signals even though they travel at different speeds. It backdates one input to match the other, so even your sense of immediate experience is partly a reconstruction. You don't notice this, of course. You live inside the output. But it means that now, as you feel it, isn't a simple echo of the external world. It's a composite, a best guess. And yet it feels solid. That feeling is what drives behavior, what makes choice possible, what allows you to plan. It's what gives your life structure, not just events strung together, but a central point to anchor around. Without now, memory wouldn't form correctly. You wouldn't be able to distinguish past from present. You wouldn't know when to act. But physics doesn't need now to work. Particles don't have awareness. They interact. They move according to forces, fields, gradients. Time is a parameter in those equations, not a moment, not a perspective, just a label. There's a deep mismatch between how we experience time and how it behaves fundamentally. Some theories try to resolve this by saying the now is an illusion. That consciousness just rides a block universe, a static four-dimensional structure where all times exist equally. We feel the present because we're located in a certain part of that block, like being on a train that only moves forward, even though the whole track already exists. But others argue that's not satisfying. Illusions usually serve purpose. So if now is an illusion, why do we need it? Why does it feel so central? Maybe it's not an illusion at all. Maybe it's a byproduct, a necessary result of how systems process information. Any conscious system needs a reference point to compare against memory and prediction. So now becomes a workspace, a zone where incoming data is merged with internal models. You need it to perceive change, to sense motion, to learn. But that workspace doesn't stay still. The system keeps updating, input keeps flowing, the frame keeps rolling, and so now keeps shifting. Not because time moves, but because we do. The now never stays because the system that generates it, your brain, your body, your attention, is always changing. This doesn't mean now is meaningless. It means it's dynamic. A moving balance point, a brief convergence. That convergence is what lets you make decisions. You can't act in the past, you can't act in the future. You can only act in the window your system calls now. And then that window moves. So the now doesn't stay, but it leaves behind structure, memory, trace, the record of having been. And in that record, time builds itself, one frame at a time, always leaving, always arriving. If you've ever flown across an ocean, you've felt it. The strange drift between body and clock. You land in a new place, the sun is up, and your watch says something that doesn't match how you feel. You adjust your schedule, your meals, your meetings, but part of you lags behind. That's jet lag, and it's simple enough to explain. The Earth spins, time zones divide it, and we track local time based on sunlight. But time zones are more than geography. They're a reminder that even something as basic as what time is it has no universal answer. Now imagine stepping far outside Earth, past the clouds, past the satellites, into space. There, the time zone problem isn't just about travel, it's about physics. The deeper you go, the more complicated the question becomes, because time in the universe is not the same everywhere. In Einstein's theory of relativity, time is not absolute. It depends on motion, on gravity, on reference frames. The faster you move, the slower your clock ticks compared to someone who's standing still. The closer you are to a massive object, the more gravity stretches your time compared to someone far away. This isn't science fiction. It's tested, proven. GPS satellites orbiting Earth experience less gravity than we do on the ground, and they move faster. Both effects change how their clocks tick. Engineers have to correct for this, relativistic time dilation, so the system stays accurate. If they didn't, your phone's location would drift more than 10 kilometers each day. So even around Earth, time moves differently depending on where you are. Now scale that up. Go near a black hole, and the difference becomes extreme. A clock hovering just outside the event horizon ticks unimaginably slow compared to one far away. From the perspective of a distant observer, it almost stops. This isn't because the clock is broken, it's because space-time itself is bent. Time runs differently in deep gravitational wells, and yet, from the clock's point of view, everything feels normal. Locally, time always flows at 1 second per second. But globally, the universe doesn't agree on what 1 second even is. There is no single cosmic clock. That has real consequences. If two astronauts are moving through space at different speeds, or under different gravitational influences, they will experience different durations between the same events. When they reunite, they may disagree on how much time passed. This isn't a paradox. It's how the universe works. Events that seem simultaneous in one frame are not simultaneous in another. That means two people, watching two stars explode from different positions and velocities, might disagree on which explosion happened first. There's no contradiction, just different perspectives. This shakes the idea of a universal now. If what's happening now for you isn't happening now for someone else, then what is now really? On Earth we ignore these differences because they're small. We build atomic clocks, we synchronize servers, we pretend there's a global timeline, and for practical purposes that's fine. But in the cosmos, simultaneity breaks down. Different observers can experience the same universe with radically different clocks. Their timelines stretch, compress, curve, all according to where they are, how fast they're moving, and what's pulling on them. So the universe doesn't have time zones in the way Earth does. It has something stranger. It has personal timelines, clocks that are not just set differently, but that tick at different rates. This leads to a strange conclusion. Two people could leave Earth, take different routes through space, and return with different ages. Their biological clocks would reflect the paths they took. And that's not because they made a mistake in tracking, it's because time itself was different for each of them. That's the twin paradox, a thought experiment from Einstein, confirmed in particle physics and clock experiments. And it shows just how flexible time can be. But now go further. Imagine a galaxy cluster 1 billion light years away. From your perspective, the light you see left that cluster 1 billion years ago. But from the perspective of someone on a planet in that cluster, watching Earth, the same is true in reverse. Each observer sees the other's past, not because of memory, but because of light travel time. Even the speed of a light, so fast it seems instant to us, is slow on cosmic scales. That means the universe, as we see it, is full of time delays. Stars are where they were, not where they are. Explosions we watch happened millions of years ago. The cosmic microwave background, the oldest light we can see, comes from a time when atoms first formed nearly 14 billion years ago. So the sky's not a snapshot of now, it's a tapestry of thens, a record of events stretched across distance. That also means the idea of what's happening now everywhere doesn't make much sense. There is no universal present in the cosmos, just local nows, connected by signals that take time to arrive. You might wonder, is there any way to define a global time? In cosmology, scientists use something called cosmic time. It's a theoretical clock that ticks for a hypothetical observer who's stationary with respect to the expansion of the universe. This observer doesn't move relative to the cosmic microwave background. That gives a kind of standard reference frame. But no real observer matches that perfectly. It's useful for equations, but in practice, everyone experiences their own version of time. And that's what makes the cosmos so strange. It's not just that events happen far apart, it's that they happen in different timelines, shaped by gravity, motion, and position. The further you go from Earth, the less sense it makes to ask, what time is it there? There is no shared schedule, no master clock, only individual histories. And yet, structure emerges. Stars still form, galaxies still rotate, black holes still grow. On large scales, the universe follows consistent patterns, but those patterns don't happen everywhere at once. There's no cosmic tick to sync to. So when you ask whether the universe has time zones, the answer is yes, but they're not geographic. They're dynamic. Not divisions of longitude, but of motion and mass. Time zones in the cosmos are curved surfaces in space-time, defined by how energy is distributed, and every object moves through its own one. You live in one shaped by Earth, by the Sun, by the galaxy. But that's just one of infinitely many. Each clock, each path, each observer moves through a unique slice of time, and that's what makes time personal, not just psychologically but physically. Each being, each atom, each photon has a different route through space-time, and each route defines what it means for that thing to age, to evolve, to persist. You can line up two watches, but you can't force the universe to agree on what now means everywhere. And so when we look at the stars and ask what's happening there right now, we're really asking, what happened long ago that we're only seeing now? There's no fixed answer, only layers, only light arriving late, only time zones that are not zones at all, but flows. We build schedules to manage time, wake at 7, work until 5, dinner at 6, sleep by 10. The hours give shape to the day, they make activity predictable, they turn time into structure. But does the universe work that way? Is there a cosmic schedule, a master plan of events, with regular intervals and known outcomes? Is the universe keeping time the way we do? At first glance, it might seem like it does. Stars are born, live and die in cycles. Galaxies spin, planets orbit. Even atoms have consistent behaviors, emitting radiation at specific frequencies. These patterns repeat. They're measurable. They're stable. That's why we can build atomic clocks that stay accurate for millions of years. Why we can predict eclipses thousands of years in advance. Why the calendar mostly works. It gives the impression that the universe is on a schedule, but there's a difference between a pattern and a plan. The universe follows laws. Those laws describe how things behave given conditions. Gravity, motion, thermodynamics, quantum fields. These rules don't set appointments, they set constraints. If a star has a certain mass, it will burn at a certain rate. If a planet sits at a given distance from a star, its orbit will take a certain amount of time. These outcomes are predictable, but not because anything is keeping track, it's just cause and effect. A schedule implies intention, awareness, a system with an internal clock that knows what comes next. The universe doesn't have that. It doesn't anticipate. It doesn't wait. It simply continues. Some things take billions of years. Some happen in fractions of a second, some events repeat, some don't. The variety is vast and the pacing is not regular across systems. When a hydrogen atom in a cloud fuses into helium inside a young star, there's no cue from the universe saying, now it's time. It happens when conditions allow, enough pressure, enough heat, enough proximity. The event occurs not on schedule but on threshold. That's true across scales. The orbit of Earth isn't fixed by a cosmic planner. It results from mass, inertia, and the curvature of space-time. The length of a day, the pull of tides, the pace of seasons, these are emergent, not ordained. And yet they create reliable rhythms. That reliability is what we use to build our own schedules, calendars, clocks, time zones. All of them emerge from observing natural regularities. But they're human tools, conventions. No one outside Earth uses a year. No one outside the solar system recognizes Tuesday. The universe doesn't label intervals. It doesn't divide time into usable portions. That's something we do. Because we need to. Without some form of structure, long-term planning becomes impossible. Coordination fails. Memory loses its framework. Time becomes a blur of unrelated events. So we carve up the flow into hours, days, decades. But the universe doesn't. It runs continuously without reference to schedules. Events happen when systems cross thresholds. A black hole forms when a massive star collapses beyond a critical radius. Not earlier, not later. A comet returns when its orbit brings it close again. Not because a clock says so, but because geometry and gravity demand it. In that sense, the universe is reactive, not proactive. It doesn't look ahead. There's no master file of upcoming events. No centralized timekeeping mechanism that says when galaxies should collide or when a planet should freeze. Just rules. Just systems following those rules. We see patterns because many systems are governed by similar dynamics. Atomic transitions happen at known frequencies. Radioactive decay follows statistical laws. These allow prediction. But even in decay, there's no schedule per particle. There's only probability. You know how many will decay, on average. You don't know which. That randomness is part of the system. It's not chaos. It's uncertainty built into how matter behaves. So even when we find regularity, it's not absolute. Pulsars, rotating neutron stars, flash in near-perfect cycles. Some are so stable that we use them as cosmic clocks. But even pulsars slow down, not evenly, not always predictably. Over long time scales, they drift. Their signal changes. The schedule fails. The same is true of stars. They seem steady across a human lifetime, but over millions of years their brightness changes, their orbits shift, their composition evolves. No two stars are identical. Their lives are shaped by mass, companions, collisions, and chance. There's no calendar behind any of it. Still, the patterns are real. The cosmic microwave background tells us the universe was once hot and dense. That light has cooled as space expanded. The expansion follows a curve, a mathematical model. We can trace it back, we can project it forward. But even expansion isn't on a timer. It's influenced by dark energy, by mass distribution, by dynamics we still don't fully understand, and we don't know how long it will continue, maybe forever, maybe not. So does the universe keep a schedule? Not in the way we do. There are patterns, yes, but they arise from interaction, not design. There are rhythms, but no ruler. No clock tower at the center of everything striking each hour. Just local processes, some fast, some slow, and all of them following the same physical rules. Our concept of schedules comes from how we live, in groups, with plans, with needs. We map time so we can act within it. The sun rises and we wake. The moon changes and we count the days. We impose cycles on what's already there. That doesn't make those cycles false. It just means they're not inherent. In the deep future, when stars go dark and the last black holes evaporate, there won't be any remaining structure to support a schedule. There will be no clocks, no observers, no predictable changes, just a quiet fade, not on a timeline but on a slope. And yet right now, in the present, we still ask the question. We still build routines. We still measure motion against motion, change against change. Not because the universe does, but because we do. And that's what schedules are. tools for living in a universe that doesn't wait. It's not easy to picture an ending to time. You can imagine things stopping. A movie finishes, a candle burns out, a star collapses, but time keeps going. Even in silence, even in emptiness, the seconds feel like they still tick past. We're used to time as the background of everything, the medium in which all change unfolds. So asking whether time could ever stop feels like asking whether space could vanish. Where would things happen, if not in time? But physics doesn't treat time as eternal by default. In fact, some theories suggest that time, like matter, energy, and space, might be something that began, something that could also end. The Big Bang wasn't just the beginning of matter, it was the beginning of time itself, as far as we can tell. Before it, the word before might not even apply. Our equations break down. The earliest definable moment marks the start of space-time. Time began when the universe did. So could it end the same way? Not with a bang, but with the collapse of structure, the decay of motion, and the erasure of clocks. The simplest answer comes from entropy. We've talked about it before. The tendency of systems to move from order to disorder, from useful energy to equilibrium, from structure to spread. In a closed system, entropy increases. Over time, differences fade, heat equalizes, motion slows. Eventually, you reach heat death. That's the long, slow ending where nothing dramatic happens. Just fewer and fewer changes, stretched over longer and longer timescales. Stars burn out, black holes evaporate, the last particles interact. Eventually, there's nothing left to change. And that might be the closest thing to an end of time, not a stop, but a fade into uniformity, where nothing marks one moment from another. You can still assign numbers to coordinates. You can still define this happened after that in some mathematical sense. But without change, without motion, those numbers stop meaning anything. If no system undergoes any transformation, then time, as we experience or measure it, has ended. That's not the only possibility. In some cosmological models, the universe might reverse. The expansion might stop and gravity might win. Everything could collapse back in. A big crunch. Space shrinks. Density increases. Clocks run faster. And eventually the whole structure folds into itself. If time began at the Big Bang, it could end in a big crunch. But current data doesn't point that way. The expansion of the universe is accelerating. Driven by something we call dark energy, space isn't just growing, it's growing faster over time. That makes a crunch unlikely. Instead, models suggest we're heading toward one of several long-term outcomes: heat death, as already mentioned, or something stranger, like the Big Rip. In a Big Rip scenario, dark energy doesn't just expand space, it tears it apart. First galaxies drift from each other, then stars within galaxies, then atoms. Eventually even space-time itself could be pulled apart. The rate of expansion overwhelms all other forces. In that case, time ends not through stillness, but through rupture. The fabric of the universe shreds, and the concept of time dissolves along with it. Both the heat death and the Big Rip are extreme ideas. They lie trillions of years in the future, beyond any scale we normally use. But both suggest an end not just to objects, but to time as a meaningful quantity. Of course, we don't know for sure. Our best models describe how time behaves given certain conditions, but they don't fully explain what time is, especially at the intersection of general relativity and quantum mechanics. There are approaches, like loop quantum gravity or string theory, that try to get underneath time. Some suggest that time might not be fundamental at all, that it emerges from deeper relationships, that at the smallest scales there is no continuous time, only a series of configurations linked by statistical rules. If that's true, then time is not something that can stop like a ticking clock. It's not something that flows at all. It's something we perceive when certain conditions are met, when systems interact, when patterns unfold, when memory becomes possible, and if those conditions disappear, if all systems lose contrast or collapse into sameness, then time as an emergent phenomenon ends, not because it was destroyed, because it's no longer needed. like a tool set down after the job is done. That's a strange idea. It feels alien, but it matches something we've seen before. In black holes, time near the event horizon slows drastically compared to the outside world. From a distant perspective, an object falling in seems to freeze just before crossing the horizon. It's still there, still moving, but its progress stalls. Time doesn't stop for the falling object. It continues normally from its own point of view, but to everyone else, it vanishes into a standstill. That shows us again that time isn't universal. It bends, slows, stretches, and possibly ends, not everywhere at once, but differently in different places. Another possibility is that time never ends, but becomes irrelevant. Imagine a future where the universe is so stretched out, so sparse, that no meaningful interaction happens for quadrillions of years. Particles may still exist, time may still tick in some abstract sense, but with no observers, no clocks, no events. Who's left to say what time even means? That's not the same as stopping, but it's a kind of vanishing. The loss of time as a practical reality. Still, that's the long view. Here and now, time continues. It holds together the sequence of everything we do. It gives structure to memory, to motion, to life. But the question of whether it will last forever, that depends on what time actually is. If it's fundamental, built into the bedrock of physics, then maybe it keeps going, regardless of what's inside the universe. If it's emergent, arising from matter and energy in motion, then maybe it fades, like any other pattern, when the pieces spread too far. And if it's only an illusion, a trick of perception, then maybe it never really existed to begin with. Only the changes did, only the differences, only the things we compare and the moments we remember. So maybe the better question is, will change ever end? And if the answer is yes, then that's when time ends too. Not with a dramatic signal, not with an announcement, but quietly, slowly, with the last change undone by stillness. You've been here a while now, not just in this recording or in this episode, but here, awake, thinking, listening, following a quiet trail through something you can't see or touch, but that shapes everything. Time. Maybe you started with a simple question. Maybe you were already half asleep. Maybe you just wanted to hear something calm, something steady. And somehow, we ended up here, still in the same moment, still in now, even after all we've covered, the clocks, the physics, the memory, the stars. Nothing's really moved except your awareness. Time didn't change for the universe, but maybe your sense of it did. And that's what this was always about. Not solving a problem, not pinning down a definition. Just sitting with something so familiar, you almost forget it's strange. You, right now, are in a moment that has never happened before and will never happen again. It's just one of many, but it's yours. All the physics, all the theories, all the thought experiments, none of them change the fact that you exist in time, not apart from it, not watching it pass, inside it, shaped by it. You breathe through it, you wait inside it, you remember because of it. And that's what makes the question matter. Not what time is it, in the sense of numbers, but what is this moment, right now? And why does it feel like something? Physics doesn't require that it does. The equations don't care about how time feels. They work whether anyone's watching or not. But your life unfolds one moment at a time. You carry the past. You guess the future. You wake up inside this narrow band of now and try to make sense of it. You wonder if it's moving. You wonder if it's real. And maybe it is. Maybe now is just what it feels like to be a system that remembers, not all at once, but in order. That's what gives you continuity, not a perfect map of the past, not a countdown to what's next. Just enough connection to know you've been here before and you'll be here again. Time doesn't have to announce itself to be present. It doesn't have to tick. It doesn't have to flow. It just has to allow things to change, to shift, to come into being. That includes you. You're not separate from time. You're not a visitor in it. You're part of what it is. And so whatever time is, it includes this, you, here, now.